You present also. So tomorrow you not come.
Em ở Đồng Nai nhưng mà hồi năm lớp 9.
เอามือจิ้มจอด้วย จิ้มไม่ได้ไงล่ะ
Hi, Hermie.
Hello, everyone.
Yes. Hi, Hermie.
Hello, everyone. Oh, Kwang Wen-shu. Professor Kwang Wen-shu is here. Yeah, welcome. So, good afternoon, everyone. Professors, young scientists. Yes. Young scientists, postdoctor, and PhD students. So welcome to the International Symposium of Young Scholars on Carbon Resources, conversion or YSCRC 2021. So I would like to introduce myself. My name is Tasha Paula, which is in. You guys can call me Mintz because my name is too long. So I am honored to be the host of this event, which has participants from China, Japan, Korea, Vietnam, Russia, and Thailand. And this is our second YSCRC, which has been extended from the first success YSCRC. The first symposium was hosted by the Shenyang University Chemical Technology, or SYUCT China, in 2018. And this is the second YSCRC, which will be held on October 14 to 16, 3 days from now, by Thammasat University Research Unit in Bioenergy and Catalysis, Thammasat University, Thailand. According to the coronavirus 2019 pandemic situation, so our symposium will be online via Zoom and YouTube platform. And the objective of Symposium is a stage of young scientists, postdoctor, and PhD students to present their work. The symposium was proposed by a group of professors in various kinds of close cooperation of chemical and thermal utilization of different carbon resources, including but not limited to coal, biomass, petroleum, natural gas, carbon dioxide, syngas, organic waste, and others. The symposium was designed to promote international academic exchange and research cooperation among involving professors and their research groups. So upon this time occasion, I would like to invite Professor Siriwan Subnukan, Vice Rector from Thammasat University, for welcome address and opening remarks for YSCRC 2021.
Yeah, thank you, Mint. Good afternoon, everyone. My name is Siriwan Sudmikan. I'm Vice Rector for Research and Innovation at Thammasat University. It is my great pleasure to welcome all of you to the second International Symposium of Young Scholars on Carbon Resources Conversion, or YSCRC, a virtual conference. It is my great pleasure to welcome all the plenary speakers, invited speakers, and all participants from various countries, as Mint just mentioned. The conference is completely conducted on a digital platform to connect all researchers due to COVID-19 pandemic. And I am very grateful to the organizing committee and participants who joined the conference to share your knowledge and vast experience with young scholar researchers on the recent trend of carbon resources conversion and their applications. Well, actually, this topic is very, very interesting and related to the SDG, from the UN. This is really, meet the the objective of the UN on the green energy. So when I look at the program at glance, and I see the list of presentations planned for the next few days, it reveals the amazing diversity of carbon resources conversion, which are a range of fundamental scientific and also engineering studies, and also industrial developments regarding relevant technologies aiming for the clean, efficient and value-added, and also low carbon utilization of carbon-containing resources as fuel for energy and as feedstock of materials or chemicals from, for example, fossil fuels, biomass, syngas, carbon dioxide, hydrocarbons, and organic waste via physical, thermochemical, biological, and other technical methods. So I would like to thank the organizing committee. Thank you, Dr. Suwadi, Dr. Shanatip, and everyone who greatly helped in organizing the virtual conference. Moreover, I would like to express my sincere appreciation to Horiba Scientific for the Best Oral Presentations Monetary Awards to encourage the young scholar for their excellent research and presentations. Before I turn over to the conference, to the chairman of the first session, I sincerely hope everyone delightful, stimulating, and networking with fruitful discussions in this conference. Thank you very much. สวัสดีค่ะ
ขอบคุณค่ะ Thank you, Professor Siriwan, for your warm welcome. For the next, I would like to invite Professor Kwang Won-soo, President of Chenyang University of Chemical Technology and Editor-in-Chief of Carbon Resources Conversion, or CRC, for opening remarks.
Okay, thank you very much. I say this symposium is well organized and did a very good preparation. Thank you very much for all the work makes this possible. Because of the special season, I think we have this second symposium where this way, somehow it's also exciting. And we meet online. Can you hear me? Can you hear me? Yes?
Yes,
okay.
yes,
Good.
very clear.
Yes, I think for this symposium and Swati did a very excellent work. Of course, we also had some discussions. I think this symposium is very good for the young scholars. Originally, actually, we planned this symposium is for the young scholars from the neighboring countries so that they can easily find ways to present their research in English and also to make friends, make the colleagues in the neighboring countries and to promote the progress in science and technology for all the young scholars. I think this is a very good way. Because of the pandemic, last year we did not have this event to hold according to the normal schedule. And this year, and Swati and also other, I think, Thai colleagues did a very excellent work, make this possible. And I think congratulations to this successful organization of this symposium. I think in the next few days, and the students, most of the presenters are students, and I believe they will present do very good presentations, and to try to exchange the ideas. I also hope, and in addition to presentation, and the young scholars should try to ask a question, try to get some questionable points to practice and to train yourself to become the outstanding scholars. I think the exchange and the communication is very important. I encourage all the young students actively participate and attend this symposium. Okay, thank you again for the excellent organization work, and hope everyone hears and safe. And I believe maybe after 1 or 2 years, we can come together to have this symposium continuing. Okay, thank you very much.
ขอบคุณค่ะ Thank you Professor Guang Wenxu for your speech, and I hope next year we will meet face to face. Okay,
Yes.
and the next step, I would like to all of you in here in Zoom and YouTube platform to know more about Thammasat University. I would like you guys to let's watch the video of Thammasat University.
Thammasat University has a proud history that spans over 8 decades. Our founding philosophy, to serve the people, has been a true spirit of Thammasat that passes on from one generation to another. At Thammasat, we value freedom of learning. First started off as an open university to provide ordinary people with higher education. Thammasat has today grown into a comprehensive institution of higher learning, offering students with world-class education and the free spirit to think, learn, and experience the world. At Thammasat, learning is exploring. As a leading research university, Thammasat offers education in a full range of academic disciplines, social sciences, and humanities. Science and technology, and health sciences. Learning at Thammasat is based on hands-on experiences, using problem-solving and knowledge-sharing approaches so that students can explore for themselves ways to solve problems. Thammasat has a far-reaching international network that spans across the globe. Our cutting-edge technology and support research facilities, combined with active learning approaches, allow Thammasat students to develop their potentials to the fullest. At Thammasat, learning is happiness. Thammasat offers fun-filled experiences that nurtures creative mind and healthy body, with a great variety of sports and recreational activities on campus. to cater to everyone's needs and lifestyle. At Thammasat, we strive for excellence. Academic excellence and cutting-edge research is well integrated into teaching and academic activities. This leads to creation of research projects that contribute significantly to the advancement of the academics as well as the society at large. At Thammasat, we take great pride in our achievements and long-standing spirits as University for the people. We'll continue to create the next generation leaders by equipping them with critical minds, intellectual caliber, consciousness of virtue, and the legendary Thammasat spirit to serve the people. Thammasat has, for 8 decades, been a place where leaders have been groomed to serve the nation and the world. Thammasat University, where we learn to love the people.
So Thammasat University is university for people. Yeah, thank you everyone for your attention on our video. But before we move to our first session, I would like all of you in here in YouTube platform or via Zoom, let's take picture together, all of us. And I saw the people from the Shenyang University of Chemical Science Technology. Hello, สวัสดีค่ะ Very good. So would you please open your camera, please? And then I will count 1, 2, 3, and we will capture the picture and smile. Okay. หลังบ้านได้ไหมคะ Okay, so everyone, 1, 2, 3, smile. Can I have one more picture? Okay. And I will count 1, 2, 3, smile. Thank you so much for your cooperation. And let's move on to our first session. We are going to talk about the waste-derived fuel profiling with coal, practical issues and solution by plenary speaker. And first, I would like to invite Professor Ding Rongbai from Shenyang University of Chemical Technology. There are Associate Professor Suwati Kongparagun from Thammasat University, is the chairman and doctor. And the next person is T. Tong Witran from Nien That Tran University, is the co-chairman.
Okay, thank you very much. Yeah. Welcome all of you. I'm Assistant Professor Suwati Kongparagun from Thammasat University. And we have our first plenary speaker, Professor Ding Rongbai from Shenyang University of Chemical Technology. Before we start the presentation, I would like to introduce you about Professor Ding Rongbai. Information. He obtained his PhD from Tsinghua University in China. He has worked on several roles with the different institutions and corporations in China, Japan, Canada, and the United States. His technical expertise includes fluidization, particle technology, fuel cell solid waste utilization, combustion, emission control, and fluidized base mineral processing. He has considerable knowledge and experience in process and product development. His recent research interests are related to the clean coal technology, combustion with ultra-low emission, and thermochemical conversion technology. And today, he is going to present about the waste-derived fuel, coal-firing with coal, practical issues and solutions. Okay, everybody, please welcome Professor Ding Rongbai.
Okay, thanks, Chair. Thanks all my colleagues in different countries in different time zones. Thanks all the organization committee members for your hard work and make this conference possible. Thank you all. And as just introduced, my name is Ding Rongbai, speaking from Shenyang University of Chemical Technology in China. And it's really my pleasure to be here today to speak about this topic. Okay, so and I'm going to talk in the next 30 minutes about the waste-derived fuel, coal firing with a coal in a commercial or pulverized coal boiler. So a little bit about the practical issues and the solutions, and share with you some of my experiences. The next one. Okay, this is just a brief outline of my presentation. So I will give a brief background introduction, and then we'll talk another two topics. The first one is how are we going to transform municipal solid waste into a fuel? And we will have the fuel. How are we going to co-fire this fuel in a commercial or fired boiler? So I conclude my presentation with a short conclusion remarks. Okay, so let's first look at the waste issues. Here is specifically called the municipal solid waste. So as you all know, the United States is a very, very wasteful country in the world. It's only 30 million people, generates about near 300 million tons waste per year. On average, about 5 pounds per day per person. Among this waste, 50% ended up in the landfills because they have vast land. Okay, in Japan, Japan does a much better job. So it generates about 128 million tons, and it's only about half of the United States per day per capita per person. And in Japan, 6% of waste is ended up in landfill. In South Asia, East Asia, and the Pacific region, we generate about total 340 million tons a year, and which occupies about 26% of the world total municipal solid waste. And based on the World Bank, this amount is going to up to about 900 million tons by 2025. So if we talk about the world cities, it's about 2.2 billion tons per year by 2025. And on your left on the screen, that's the Beijing. And those marks is the landfills. You can see the Beijing city downtown is surrounded by the landfills. Okay, so we generate so much waste, and some of the waste most of it ended up in the landfill. I guess nobody really likes landfill because landfills cause air, water, soil pollution. They emit CO2, CH4, these are greenhouse gases. And of course, this use lot of energy contained in your waste. And the landfill occupies a lot of airspace and also causes the wastewater issues with the rainfall. So another way to handle the waste is certainly with the incineration. So here I use the incineration, please take attention to that, okay? Because in the United States, the incineration is not equal to the combustion. So incineration, if you have an incinerator, it's regulated very strict regulation rules, six-way rule. And everybody knows if you burn the waste in incinerator, you generate the dioxin and the furans, which is very, very harmful to our human health and the environment. And there causes serious corrosion problems in the boiler because of this, because it has a higher content of chlorine in our municipal solid waste, the PVC, plastic, and the salt in our food waste. So this forces boilers to operate at a very low temperature and pressure. So that's we generate on average, in the best case scenario, the power generation efficiency is only 20%. And the ash generated by the incinerator is a hazardous and also whenever you build an incinerator in a community, it's not welcomed by the public. Okay, on the other hand, we have the coal issues in this world, and everybody knows that coal generates the air emissions, the pollution, CO2 emissions, and especially it's attributed to the climate change. Nowadays, everybody is talking about. But in my personal view, and the coal-fired power plant maybe is better than what you really said, because in today's world, there's about 2,000 gigawatts of power is generated by the coal. It supplies 40% of the world's electricity. And in this world, we have almost 80 countries relies on the coal power generation, especially in South Africa, China, and India. Over 70% of electricity is supplied by the coal. And the coal-fired power plant generation efficiency on average today is over 40%. When you get to the super critical conditions, close to 45, 46% today, versus only 20% of power generation by the incinerator. Okay, so it seems if it's a good perfect match if we can coal-fire MSW in a coal-fired utility boilers. So because chemically and physically they just compensate each other. And on this table you can see from the combustibility and the ash chemistry, power efficiency, and power construction, and the emission, and so on and so on. And they're just a perfect match. But you cannot burn a fuel, or you can only burn fuel, but not waste in a utility boiler, based on the United States EPA's rule. So what is a fuel exactly? Why we cannot burn the waste in a boiler? Because we have to burn fuel. So what is a fuel? So on this table, you can see chemically, a fuel must be predictable and controllable, and it has to be consistent in chemical composition and higher and heating value, and it has to contain less combustion prohibitive elements. And for example, what's called the fuel? Coal is a fuel, wood is a fuel, natural gas is a fuel, and the MSW is not a fuel. And the refuse derived the fuel, RDF, is not a fuel. And in the United States, fuel and the waste combustion are regulated by different rules. So fuel must be consistent and homogeneous, chemically and physically. So that is the fuel. So this comes to the question, how we're going to transform a fuel, a waste, to the fuel. So to transfer the fuel, to be called the fuel, we have to meet 3 basic criteria. So the first, the fuel has to be homogeneous and consistent in both physical and chemical characteristics. And the second one, the fuel must meet the requirements for the specific application without negative effects on the existing process. And the third one is as an enterprise of the company. When you make the waste into the fuel, you have to make money and you have to make a profit. So that is in terms of how are we going to transform a waste to the fuel. Okay, the field in the mini solid waste is very complicated, and you have different items in the waste in the garbage bin. But if we sort that material into basically two big groups, first one is a plastic based, the resin and plastic, and second one is a fiber materials, contains say the newspaper, office paper, and cardboard, and the yard waste and the food waste and all those biomass-based materials. If we classify the material into these two big groups, we can see the hydrogen content, the carbon content for each group is relatively constant. So this gives us an idea how we are going to make a fuel to make sure the fuel is chemically consistent. So we adopt a technology using the optical sorting. So sorting the waste material into two class of materials. First is the fibers and the second the plastics. For the fibers and the plastics, the carbon content, the hydrogen content, and as well as heating value are relatively consistent. So when we separate the material into these two groups, and then we remix, metering, and remix based on what's the required ratio. And then we go through the fuel processing process. So we can finally make engineer the fuel with consistency in chemical composition and the heating value. So the bottom chart shows the higher heating value for different samples we made in the factory. So you can see that regardless of the time you make the fuel, the heating value of the fuel are always relatively constant. Okay, so and the next one, and we bring this fuel to a specific application. We need to know what's the sweet spot. So where the fuel meets the application the best. So this gives your idea. On the left axis was the hydrogen to carbon ratio. The X is the oxygen to carbon ratio. And on the right side of the axis, that is the adiabatic flame temperature. So what's see the fluidized bed or the fixed bed reactor combustor. What's your desired operation temperature. So and then what's the air combustion ratio and what's the fuel ratio you require. So you can basically adjust this different components mix and to give you the required temperature and the required chemical composition and the heating value as well. Okay, so we made the fuel, and now we have to produce the fuel. We need to produce the fuel, and so we have a huge challenge here. So and how to dry in the fuel and how to granulate the fuel, and the drying as waste content in the plastic film and the paper in the garbage bin usually has a higher moisture content. So drying is very expensive if you use the thermal drying. And the second one is you make this two-dimensional paper and the plastic film to small size to be able to combust in a combustor is going to be difficult. Okay, so on the upper side you can see what's a plastic film. When you plastic film in a granulator, they just simply melt, and then you just not kind of cut that through. And if you use the paper in a granulator, see, they make it like a cotton. It's a very fluffy, and you cannot handle, you cannot fit this into a boiler. So it looks like it's easier said than done. That's what I mean. And it's really hard to make those materials to small sizes. So how am I going to make this? Okay, so now we have the plastic and
听不到了。What's the problem? Internet.
So it's okay now, Professor.
Okay, okay.
Professor Bai, are you okay? I didn't heard like your presentation from my side. Professor Bai, I'm sorry. I think maybe we have the problem about the connection. So could you present the page again? Now I see your presentation slide as solution to the coarse granulation and densification.
你们能听到吗？ Can you hear us? 但是我们听不到你说话，你是 mic 有问题。Problem with the mic. You can hear us, but we cannot hear you. It's a problem with your microphone. Okay? The microphone has problem. 你们那个 mic has problem. We cannot hear you. Cannot hear you. I just hear you from telephone, cannot from a computer 啊。这你们的 mic 是不是把 mic 的耳关了，还是那个耳的问题啊 ？Hello， 那这还是不。
Hello, Professor Bai, you hear me?
Turn off the meeting.
For now, I didn't see the slide at the moment. Could you share the slide again, Professor?
Slides 表示不出来啊，这个然后又看不到你的屏幕了。那 OK, maybe you should check. We switch to a larger presenter. Okay, maybe later when you get ready, just tell somebody. Okay.
Oh, okay.
Okay.
Okay, so.
Buddy, I think
yes.
The internet in SYU city has some problem. Yeah, I think maybe you can first switch to the next speaker.
Okay, to the next speaker, and then Professor Bai will continue.
Yes, I will
from
connect
the
to telephone, And because now I'm in Nanchang, in a larger city, I'm not in university. Therefore, I will contact them, and when get back to normal, I will inform you. Okay.
Okay, so there is some technical problem. I apologize. And then I will switch to session 1. And about session 1, maybe I introduce a little bit. We have, I'm a co-chair of this session, and also Dr. Thi Thuong Vi Tan. Dr. Thi Thuong Vi Tan, could you show your camera, please? Could you turn on your camera? So I will introduce you. She's from Nguyen That Tan University, and she's co-chairman. Hello, good afternoon.
Yes,
and
good afternoon.
We have one invited speaker in this session, and we have 6 presentation for this session. And the session will start, I think since we move up a little bit, so maybe I start from our invited speaker in our session, Professor Tomo Mizukaki. And before we start, I will introduce a little bit about Professor Tomo Mizukaki. He received his PhD from Osaka University in 1999, working under the direction of Professor Kiyotomi Kaneda. After his PhD, he joined Professor Kaneda's group as an assistant professor. Then in 2007, he joined Professor Jisukawa's group as an associate professor. He has been promoted a professor in Osaka University from October 2019. His research focuses on the development of the high-performance heterogeneous catalysis for transformation of biomass-derived chemicals. Everybody, please welcome Professor Mizukaki.
Thank you, Dr. Sawadi-san. So I'll share the slide. Okay. Okay, can you hear me?
Yes.
Okay. So thank you very much for kind introductions. First of all, I'd like to thank organizing committee and Dr. Sawadi Sensei and Janatip Sensei for giving me a very nice chance to talk up my recent work in this symposium. So today, I'd like to talk about this valorization of biomass-derived oxygenate compound various CC bond cleavage using sodium oxide supported metal catalysts. So as you know, recently the chemical processes using biomass is highly desired because to reduce the carbon dioxide accumulation in the airs. So to reduce or keeping the amount of the CO2, we have to develop a new catalyst and new chemical processes using biomass. So from the standpoint of green sustainable chemistry. In this slide shows the biomass-derived top 15 compounds. This is proposed by the United States Department of Energy in 2004. So this, as shown here, is 3 carbons or 4 carbons and 5 carbons and 6 carbons compound are proposed as a valuable platform chemicals. So these compounds contain 3 to 6 carbons, and they also have a high oxygen content. So to utilize these platform chemicals to a valuable chemicals, we have to remove the oxygen content from these compounds. So in our group, we are recently developed several catalytic system as shown here. So starting from these platform chemicals, C3 carbons or 5 carbons, and also some sugar, C5 or 6 compounds to form the diols or diol compounds or isomerization or hydrogenation compounds, and including the reduction of the sugar molecules. And also, we are interested in to develop the CC bond cleavage reactions using the some cerium catalysts to give starting from the glycerol to ethylene glycol and the ribulinic acid to 2-butanol. So CC bond cleavage of ribulinic acid is very interesting, and the ribulinic acid is obtained from the plant biomass. And using this ribulinic acid and the CO bond scission gave this gamma barrel lactone as a cyclized lactone compounds, and the hydrogenolysis and the hydrogenation reaction to give 1,4-pentan diol, and also the dehydrative cyclization to form the 2-methyl tetrahydrofuran. These compounds are very variable and usually produced from the petroleum feedstock. And as shown here, the CC bond cleavage scission reactions, we have developed the 2-butanol production from the C5 ribulinic acid. Using this ruthenium cerium oxide catalyst gave this 2-butanol in high yield, up to the 85% yield. So 2-butanol is a very useful chemical for solvent or perfumes or precursor of methyl ethyl ketone. It's also a very useful compound. The conventional method for the access to 2-butanol is a hydration reaction of butanes. This is a petrochemical process. The also fermentation process is also now starting from the glucose. But glucose is known as an edible biomass, and this fermentation process to yields a very low amount of the 2-butanol. So the chemical process starting from the abundant ribulinic acid to butanol is very attractive. And the advantage of this approach is using the sustainable feedstock, and the ribulinic acid is non-edible biomass. So we have developed the ruthenium ceria catalyst for not only the ribulinic acid and the various type of some oxygenate compound to reduce the oxygen content by CC bond cleavage. This shows the preparation and characterization of the ruthenium ceria catalyst. Impregnation of the ruthenium trichloride solution onto the cerium oxide, and drying and calcination to form the ruthenium ceria as a brown powder. This shows a TEM image and X-ray diffraction patterns and the ruthenium KH exaspectra. All these characterizations, we can conclude that ruthenium oxide species are highly dispersed on the cerium oxide nanoparticles. Using the ruthenium ceria catalyst and checking the supporter effect. As shown here, the ruthenium ceria, zirconia, titania, hydrothalcite, silica, magnesia, aluminate. Among these catalysts, only ruthenium ceria shows a very high yield of 2-butanol. And the zirconia, titania afforded the moderate yield of the 2-butanol. And the other supports, silica, magnesia, alumina, is not a good catalyst for 2-butanol formation. In this case, the gamma barrel lactone, the cyclized compound, is a major product. And the entry 8 to 11s, we check metal effect, rhodium, platinum, iridium, and palladium. All these catalysts did not give the 2-butanol. The major product is the gamma barrel lactones. So we can say that ruthenium ceria is the best catalyst for this CC bond cleavage reactions. And interestingly, in this catalyst system, the GC analysis of the gas phase, we can see that only the methane is formed. No CO and no CO2 was observed. So in this case, the CC bond cleavage and the rest of the one carbon is formed the methane. It's also useful as a fuel. And the solvent effect is also very interesting. Only water gave the 2-butanol, and the other organic solvents, 2-propanol, 2-propanol, THF, and dimethyl-SN, 1,4-dioxane or dodecan, do not give 2-butanol. The major product only is gamma barrelolactone. So we can say that ruthenium serie and water is indispensable for this CC bond cleavage. The catalyst is a heterogeneous catalyst, and it's easily recovered from the reaction mixture by centrifugation. And the Lewis experiments show that almost no decrease of the catalytic activity after second Lewis experiments. And the previous reports forming the 2-butanol from ribonic acid, only one paper, one patent was observed, reported, ruthenium titanium catalyst. But in this results, the very high pressure of hydrogen is necessary, and the yield of the 2-butanol is low. So at this time, the ruthenium serie is the best catalyst for 2-butanol formations. To check the reaction mechanisms, we check the time course, time profile of the reactions. As shown here, the gamma barrelolactone seems to be the intermediate, and also 1,4-pentadiol is also intermediate for this reaction. After 1, 2, or 3 hours, the 2-butanol is formed, as shown here. Starting from the gamma barrelolactone or 1,4-pentadiol, these compounds also gave 2-butanol in very high yield. So we think that these compounds are intermediate for these reactions. So after the reaction, the ruthenium serie catalyst was morphology is much different from the starting fresh catalyst. The FE-SEM analysis shows that the particular ruthenium serie catalyst, but after the reaction, it seems that the rod-like structure of the catalyst was formed. The TEM analysis also shows that the cerium oxide seems to be changed from particular serie particle to rod-like structures. The cerium L3H then shows the cerium species all reduced from tetravalent to trivalent states. And the XRD pattern also shows that cerium oxide before reaction was completely transformed to cerium hydroxide after the reactions. And also, starting from this diol intermediate without hydrogen pressures, also gave 2-butanol in stoichiometric amount with ruthenium content. And IR spectra shows ruthenium CO species. So we think that CC bond cleavage occurred from the decarbonylation step. And this shows the reaction mechanism for these reactions. The ribonic acid is reduced by ruthenium serie to form this compound, and the further reduction to aldehyde. Decarbonylation of this aldehyde to give 2-butanol. The ruthenium CO species is hydrogenated to methane to form to complete catalytic cycles. And the gamma barrelolactone and the 1,4-pentadiol is intermediate. This is an equilibrium with this intermediate compound. So this catalyst is not only useful for ribonic acid, other biogenic compound is also cleaved by adjacent to the carboxyl group. Not only the carboxyl group, this polyol compound also cleavage to give a diol or monool compound. Not only the alcohol and carboxylic acid ester compound function is also reduced to give this product. So this is a summary for the ruthenium serial catalyst system. But ruthenium serial still requires a pressurized hydrogen. So we want more greener methods without H2. The next try is dehydroxymethylation, also CC bond cleavage adjust to the hydroxymethyl group. So we think that the dehydrogenation reaction to form the aldehyde and then decarbonylation gave such CC bond cleavage product. Until now, the reported catalyst system, the palladium homogeneous catalyst system. But this catalyst system requires some additives, and the use experiment is not available. And the ruthenium serial titanium catalyst also useful, but the hydrogen pressure is necessary and the high temperature is required. We developed the palladium serial catalyst. The preparation is very easy. So impregnation starting from the palladium acetate. These characterizations, palladium oxide species is highly dispersed on cerium oxide. This catalyst in the reaction of the 1-decanol to nonane, the high yield of the nonane product is obtained. In this case, we don't need hydrogen pressures, only air is useful. And after time course of the 1-decanol reactions, this catalyst system, starting from the PD0 species, it is easily reduced to PD0 species, and the reaction smoothly proceeded with the palladium 0 species. Considering the reaction mechanism, proposed mechanism is here. First, alcohol compound substrate, it can reduce the palladium species to form the palladium nanoparticle. And then the cerium oxide is also slightly reduced. And the reduced cerium species, it's also activates the primary hydroxyl group. And the dehydrogenation occurred on the edge of the palladium particle and the serial surface. And after the beta hydride elimination from the alkoxide group to form the aldehyde, and this aldehyde is decarbonylated to form the CC bond cleavage product, nonane. And then the CO species is partly oxidized CO2, and most of the carbon species is obtained as a CO molecule, and the hydrogen is formed. This catalysis system is also applicable for various types of the biogenic compounds to reduce the oxygen amount. And using this catalyst system, we try to form the ethylene glycol from glycerol. So glycerol is very useful from the biodiesel production. We tried to use the PD serial catalyst for glycerol conversion. But the pure glycerol is very difficult to cleavage to here. So we changed the next step. So we use the acetone as a modifier of the glycerol to form the soluketal using this titanium monolinite solid acid catalyst, and then using the palladium serial to cleavage of the CC bond to form the dimethyl deoxyran compound, and then the hydrolysis of this compound with the titanium bond, the same solid catalyst, to form the ethylene glycol in 75% yield. Oh, this catalyst system is developed by our group, and acetone is recyclable. So we can say that this ethylene glycol formation from glycerol is a very green new approach. Okay, so let me summarize my talks. So we want to show the sincere thanks to financial support for JSPS Kakenhi and NEDO, or some foundation, and technical support from our universities and the Spring8 for exhaust analysis. This result is carried out in our group. I'd like to thank our group members for these nice results. Okay, thank you for your attention.
Okay, thank you very much, Professor Mizutaki, for your nice presentation on the valorization of the biomass. Okay, for now, we have about 5 minutes for question and answer. Are there any questions from the participants? Or you can type the question in the chat box also in YouTube as well, and then I will ask Professor Mizutaki for your question. Okay, let me check in the chat box for a moment. Okay. Professor, during waiting for the question, okay, yeah. For me, I have a question that you study about the metal loading, right, over the various type of the metal support. Oh, sorry, I will mute some microphone for a moment. Okay, so I have some question that how you utilize the catalyst to be selective to the product according to the metal loading and also the type of the support that you're going to use.
So for example, so we usually scrutinize support material, but one of the point to select the support material is acidity or basicity, and also the specific surface areas. And in this case, the cellular has a basic support and also has some Lewis acidity. And zirconia also has a base site and acidic sites, and the titanium is also similar properties. So, but the hydrothalcite is now as a strong base support, and also magnesia is also. But silica or magnesia, I'm not sure why the silica or magnesia is not so effective. Alumina is also. But probably in these reactions, the key point is the decarbonylation reactions. And also the gamma barrelactone is an intermediate compound. And first, starting from ribulinic acid, the keto function is very easily hydrogenated to form the hydroxyl group. This hydroxycarbonic acid is easily cyclized to form the gamma barrelactone. And once GVL is formed, this is very stable and very difficult to reduce. But the cellular, in this case, the cellular is reduced to cerium hydroxide, very strong base. So the equilibrium to the cyclization or the hydrolysis to form the linear form is also occur. So this is a point of one reason for the high activity of raceme cellulose. And another point is this rhodium, platinum, iridium, palladium, it also gives GVL as a major product. But this metal species, the decarbonation also occurred. But the metal CO species is very stable, and it's difficult to remove under this condition. So the catalyst is poisoned by CO. Okay, so the only ruthenium species is a very high activity for methanation of the CO, metal CO species. So that's the reason for the very high activity of this ruthenium series catalyst. Okay.
Okay, thank you very much, Professor. Okay, let me check in the chat box for a moment that any question from the participants or not. Okay, so we still have 1 minute for short one question. Are there any questions from the participants? Okay, I think there's no question from the, okay, one more question. Professor, can we change the normal metal to transition metal?
Oh, okay, so you mean as a non-noble metal? Maybe so.
Yeah, I think so. In the chat box, yeah. Transition metal in this case is ruthenium, platinum, right? Rhodium, iridium, and palladium. So I think the participants would like to know, are there another metals that would be loaded over the metal oxide support and work well with this reaction?
Maybe the question is change to noble metal to transition metal. That means, I guess, the non-noble metals such as nickel or cobalt or sand. Yeah. We have also checked tried some prepared catalyst, nickel seria or something, and because nickel is known as a methanation catalyst for carbon monoxide, but under these conditions, nickel seria is not good for the CC bond cleavage reactions, probably due to their instability to water solvent, I guess so. Okay.
Okay, yes, Professor. Okay, for now it's about the time for the first session from our invited speaker for today. I would like to thank you very much for Professor Mizutaki for joining us for today and share your idea about the valorization of the biomass derived oxygenated via the carbon double bond cleavage. Thank you very much, Professor, for your nice presentation. Thank you.
Hey, thank you very much.
Okay, for the next speaker is Miss Nishabun Chaihat from Hirosaki University. Okay, Nishabun, could you please share your slide? And today she will present about the in situ catalytic upgrading of bio-oil derived from pyrolysis of the biomass over the hollow HSM5 zeolite. And you have about 10 minutes for question and answer. Okay, please.
Good afternoon, everyone. My name is Nishabun from Hirosaki University. The presentation for today will be about in situ catalytic upgrading of bio-oil derived from pyrolysis of biomass over hollow HCSM5 zeolite. Let's start from the introduction. As we have known that the CSM5 is widely used for catalytic upgrading of biomass and show good performance for aromatic production. However, its micropore limit the diffusion of the reactant and products pass through these micropores, resulting in the raw aromatics productions. To overcome this problem, hollow structure CSM5 is the one choice for solving the diffusion limitation reported in many works. However, it is very new for catalytic upgrading of pyrrolite bio oil. Moreover, the hollow structure CSM5 normally needs 2 steps for synthesis. However, in this work, we can synthesize it in the one-part synthesis using the simple hydrothermal method. So our objectives are to study the effect of synthesized hollow HCSM5 and apply it for catalytic upgrading of bio oil derived from fast pyrolysis of biomass, including cellulose, hemicellulose, and lignin. And we expected that it could produce higher aromatics when compared to the original structure CSM5. And this slide shows the preparation of catalyst will be start from the mixture of TaOH or theta-ethyl orthosilicate, TPaOH or theta-propyl ammonium hydroxide, ammonium nitrate, sodium hydroxide, and water. The molar ratio are different depending on silicon to aluminum molar ratio, and the key step of this synthesis is the hydrothermal treatment at 170 for 3 days. And for the hollow HCSM5-TP is the parent hollow CSM5 obtained from this step. Further treat with the TPaOH in order to obtain hollow structure with the mesoporous shell. And for the solid CSM5 also prepared for comparison. Is prepared following this step without sodium hydroxide adding. And all catalysts were applied for catalytic upgrading using PYD-CMS and fixed bed reactor. The reaction temperature were used at 500 degrees C for 3 minutes. This slide shows TM image of our catalysts, including the solid HCSM5, hollow and hollow CSM5 with different silicon to aluminum ratio. We can see that the morphologies of our catalysts have quartz-sized rectangular shape, and we can see the hollow in the center of each particle for our hollow catalyst, while the solid CSM5 has a uniform solid morphology. More interestingly, the many mesopores were formed after the treatment of TPaOH solution, which were expected to be useful for providing more active sites and distribution channel for the upgrading of bio oil. And this slide shows the nitrogen absorption, desorption isotherm, and the pore size distribution. We can see that for the solid CSM5 exhibited type 1 isotherm, which correspond to micropores, while our hollow CSM5 catalyst show type 1 isotherm and H4 type hysteresis loop, indicating the existence of micropores and mesopore in the structure. And we can see that for the hollow 30TP has the largest hysteresis loop and the high volume of pore here. This confirms that the hollow 30 further treat with the TPaOH provide a large number of mesopore. And when we see the textural properties in the table, solid HCSM5 show the highest surface area with the highest microporous surface. Furthermore, the additional TPaOH treatment for hollow 30 can maintain a similar high surface area as the original hollow 30. This slide shows the ammonia TPD profile of our catalyst. There were two ammonia desorption peak at the low temperature and high temperature belong to weak acid size and strong acid size. In the table show that the total acid amounts were decreased when increasing the silicon to aluminum ratio because the partial removal of aluminum species formed the framework during desiccation step. Among these catalysts, hollow 30TP has the highest acid amount, which suggested that the formation of mesopores resulted in a higher acid amount with the higher accessibility to the acid size. This slide shows the chemical composition in upgraded of bio oil with the horo catalyst using PYTCMS. In the cases of cellulose and hemicellulose, horo 30 produce the highest aromatic hydrocarbons when compared to different silicon to aluminum ratio samples. However, for the horo 30 TP, further promoted the formation of aromatics higher than the parent horo 30. This implies that the horo structure which mesopores on the shell promoted the reactants and products, access more active sites and diffuse from the structure more easily. Meanwhile, horo 30 TP showed the negative effect in the case of lignin due to components in lignin cannot effectively diffuse in the rich mesopore of horo 30 TP. Moreover, after we knew that horo 30 TP was the best catalyst for cellulose and hemicellulose, while the horo 30 was the best catalyst for lignin, then we also studied the effect of the use of biomass to catalyst weight ratio or B2C weight ratio on aromatics production using the fixed reactor and determined the liquid product using GCMS. And the results show that the relative peak areas of aromatics were increased accordingly as the amount of catalyst increases. However, signal peak area which reflected the relative aromatic yields didn't increase obviously when increased to 1:4 ratio. It suggested that the aromatic products were limited since the use of 1:2 ratio, and it implied that the aromatics wouldn't increase for 1:4 because they might be converted to polyaromatics or coke through secondary reactions such as condensation or polymerization. This slide shows mass balances and gas production. In the cases of the cellulose and hemicellulose, when increasing catalyst amount, gas and water yields were increased while the bio-oil yields were decreased, and its opposite in the case of lignin, gas yields were decreased as the B2C increases. This increased amount of catalyst promoted decarbonylation, decarboxylation, and various hydrocarbon conversion reactions such as cracking and aromatization. For the conclusion, the horo 30 catalyst further treated with the TPAOH results in the highest catalytic activity for the upgrading of bio-oil derived from cellulose and hemicellulose pyrolysis wafers. It exhibited the conversion of oxygen-containing pyrolytic wafers and to the highest relative amount of aromatics. And the scale up of the experiment using a fixed reactor showed that 1:2 was the optimum biomass to catalyst weight ratio. That's all of my presentation. Thank you. And I can show a little bit about this support. This slide shows that the 1:4 ratio can promote the polyaromatic hydrocarbons. This slide shows the XRD pattern of all catalysts, and this figure shows the SEM image. And this slide shows the formation mechanism of horo 65. That's all of my presentation. Thank you.
Okay, thank you very much, Nishabun, for your nice presentation for today. Are there any questions from committee and participants? We still have time for one short question, and after this, I will speak back to Professor Ding Rongbai again because the condition in China is
a
okay.
question.
Yes, please.
Yes.
Thank you much for your nice talk. It's very interesting. I would like to know about the coking on your catalyst.
Coking?
Yes.
Let me show. Yes. Can you see the slide? Yes, for the coking, when increase the amount of catalyst to 122 and 124, it show the higher coke formation on the catalyst.
Okay. Have you ever tried about the reusability of your catalyst?
Yes, I tried. I already studied about the reusability and regeneration of catalysts, but I didn't show in this presentation. But for the results is suggested that like when using the 1:2 weight ratio, compare using Horo 30 TP compared to the original System 5, it can reduce coke formation. But I didn't show in this presentation. Yeah, so that result is confirmed that the hollow structure System 5 can reduce the coke formation on the zeolite.
Okay, thank you.
Thank you so much.
It's about the time for Nishaboon. Thank you very much for your presentation. Okay, and the next speaker, I will back to our plenary speaker, Professor Ding Rongbai, for the presentation. Professor, please share your slide. Okay, I see your slide now. Okay. Yes, Professor, you can start your presentation.
Huge. Okay.
Okay.
This is okay?
Yes, it's okay. The signal is okay now.
Okay, thank you very much. And I'm sorry for the technical problems. And okay, so I think everybody probably already know the introduction, so I will skip this.
I think you started the point, you stopped.
Okay. Is here those? So let's go over the first of a few slides fast. So this is the outline of my presentation, and I'm going to give a little bit of background description, and then we'll talk about how to transform municipal solid waste into a fuel, and talk about how are we going to co-fire the fuel in a commercial tea-fired pulverized coal boiler. And then they will conclude with a few conclusion remarks. So let's first look at the waste issues. So as everybody knows, the United States is a wasteful country in the world. It generates about 220 million tons of municipal solid waste a year. On average, it's about 5 pounds per day per person. And among this waste, about 50% ended up in landfills. And Japan is a pretty good country and only generates about 2.1 pounds per day per person. It's less than half of the United States on average. So the South Asia and the East Asia and the Pacific region, so we generate about 340 million tons a year, and which is about 26% of the world total. So, but according to the World Bank, and so this amount is going to be up to about 900 million tons by 2025. So if we talk about the world cities, there's about 2.2 million tons, a billion tons per year by 2025. So this is a huge number of the waste is going to be generated. On the right screen, that's a Beijing city I show you on the map. So surrounding the landfills, you see the downtown Beijing is pretty much surrounded by the landfills. So this is becoming a serious issue. One of the solutions to handle the waste is landfill. And, but I guess nobody really likes a landfill because landfill causes a number of issues. So first of all is the air, water, and the soil pollution because of the landfills. And also it emits the CO2 and methane. That's greenhouse gases. and the energy contained in the material will be lost as well. So plus they will occupies a lot of airspace, and with the rainfall, it will generate tons, million tons of wastewater. So that becomes a serious concerns as well. So another way to deal with the municipal solid waste is by the incineration. So, but the incineration in the United States is regulated by the various strict environmental rules. They're called the commercial and the industrial solid waste incinerator rules, CISWIS. So, and also incinerator will cause air emission, particularly and dioxins and furans, so which is very harmful for human health and environment. They also cause serious corrosions in the inside the boiler and the downstream equipment. So to minimize the corrosion and caused by the chlorine content and like the PVC, plastics, and the salt in our food waste, so that the boiler has to operate at a lower temperature and the pressure. So the power generation efficiency for the incinerator-based power plants is only on average about 20%. And the ash from the incinerator is classified as hazardous. And also everybody probably know whenever you want to build construct a new incinerator power generation plant, so you will get a big public issue and objected by the public. So on the other hand, our world has an issue with the coal, and the coal, and everybody complains coal power plants emits the SO2 and the CO2 and etc. But we have to realize the coal power plant is still the dominant power supply for electricity, and the world today has a total capacity of 2,000 gigawatts, which on average is 40% of the world's electricity. And there are 80 countries rely on coal for power generation, particularly in South Africa, China, and India, all those developing countries, and the coal power supplies over 70%. Like the South Africa is over 90% of power is supplied by the coal. And compared to the waste incineration, coal-fired power plants generation efficiency is much higher. It's about twice higher, on average over 20%. So it seems for us, if we can coal-fire the MSW in the coal-fired unit boilers, and from the combustibility and the ash chemistry and power efficiency, all those aspects, and it seems it's a perfect match. And also, we do not need to build and construct a new power plant to burn the MSW, because the coal power plant is big enough to deal with all the municipal solid waste generated. However, in some area, especially the United States, you cannot burn waste. You can only burn fuel in a utility boilers, the EPA's regulation. So what is a fuel exactly? So, and as this table, you can see the fuel must be predictable and controllable. You have to have a consistent homogeneity in the heating value, and contains less prohibitive materials. The size, the shape, the density has to be consistent. For example, the coal, wood, and the natural gas, those are called fuel. And the waste, especially the municipal solid waste, and the refuse derived fuels, RDF, are not the fuel. So as a result, so those fuel and the waste are regulated by different environmental rules. So, in one word, if you call something a fuel, that has to have a consistent and homogeneous chemical and physical properties. So that's to see if we want to burn municipal solid waste in the commercial boiler, utility boiler, you have to transform the waste into a fuel. So to meet this goal, and the fuel has to be homogeneous and consistent. And also the fuel has to supply to meet the specific requirements of the application without negative effects, such as you cannot cause the boiler for corrosion, slugging, and lower efficiency, and so on. And also, when we're doing this process, the company or the enterprise has to make a profit. And so that's can be sustainable. So if we really look at the garbage bin, as everybody experiences, you can see the different items contained over there. And it seems too very complicated. But if we look at the waste chemically, so, and there basically have two classes of materials. The first class material are made of plastics and resins, and as a rubber, and those of synthetic materials. Another is naturally occurred wood or the biomass, and this type of material, that's a wood yards, wood waste, and forest waste, yard waste, and food, newspaper, and cardboard, and all those materials. And if we classify the material into these two groups, each group has relatively consistent of carbon content, hydrogen content, and as well as a heating value. And therefore, this gives us an idea, and we can first use an optical sorting technology to sort the material into two groups. The first is called the fibers, which have a carbon content 30 to 45%, contain about 6% hydrogen and 8,000 BTU per pounds. And another group of material called synthetic plastics, and the contains about 65 to 85% of carbon, about 10% of hydrogen, and over 17,000 pounds BTU per pounds. So we have these two groups separated, and then we can mix according to the required ratio. If what chemical composition or heating value we want to have, so we can remix this material and make that a fuel. So on the bottom of this chart, you can see the bar chart. That is the higher heating value for the samples we produce in the laboratory or in the factory. So you can see whatever from the time, different times and different season. So all the heating values per period have almost a similar heating values as it meets EPA's requirements for the consistency. So, and now we move to design the fuel chemically. So if we want to design a fuel, has a certain amount of heating value, and based on the combustor's requirement, see you burn grid fired or your fluidized bed or pulverized coal boilers. Depends what's exactly what your requirement is, and we can select the carbon chemical composition based on this chart to see find your targeting sweet spot. Okay, so now we have a way to produce a consistent fuel, but how are we going to make it? So this chart shows you some difficulties or the challenges we have. So first of all, is drying. So wool waste, the waste and the plastic film, all those major components, this material are not recyclable. Okay, there's non-market, it cannot market it, and nobody wants this. So you can only get this into a fuel. But those fuel usually contains a higher moisture of content. So using thermal drying is going to be very costly. And so this is the one challenge. And the second thing is this material is usually it's two-dimensional, like the paper, it's a sheet material plus film, it's sheet paper. And it's not the core, it's a cubic. And so these two-dimensional materials and the soft and the brittle and elastic, it's hard to break down to the size we can feed into the boiler. So for example, if you granulate the plastic film, some plastic film is melt at a lower temperature. So you can see as the granulator gets a carbon and that's it's not going to work. And the second, if you use the paper, you granulate the paper. So make very fluffy, like you make the cotton. So this cannot be handled and put into the feeder and into the boiler. So this is not going to work either. So really is that even we have the consistent field in chemical properties, but it's either said and then done, you make it. So this is a challenge. So the next one, so how we're going to do this? So we found we can first granulate the plastic fibers to a coarser particle, and we do not need to granulate it to the final size at the first step. And the secondly, we use a cutting, drying, and the machine that do the cutting and the drying simultaneously to avoid the plastic thermal melting. And the third approach is using densification first. So we'll hope of fine gradient in the later stage. So this was the way we found this way. And this gives you a few videos to see what on the top, that's the plastic as a pellets. So that's a bit of the waste. So it's really because of very soft and elastic and fiber structure is really hard to break down. And the next one is the core, and the see is use a hammer, and because the structure of a core is brittle, it can be very easily to be pulverized, and so that's the size reduced. So that makes another second issue, and we have the pellets, but we cannot fine grading the pellets. So this is the commercial pulverizer, and all the pellets you feed into the pulverizer are rejected. So we cannot make that using the commercial pulverizer. We have to use this special pulverizer, which is with a toothed discs, and there's a very sliced chamber, and uses cutting knives to cut the material on the bottom, surrounding the chamber. There's a screen, and whenever the particle size is granular to the size and can pass through the screen, so will be removed and removed by the air. So the air cooling assisted the cutting and cool down the process, and you avoid the oversizing of the material. And in this way, we can really pulverize the material to whatever the size we want. And this solves that issue. Okay, so now we have the fuel meets the EPA standard. We can make the fuel and we can feed into the boiler. So what's the issues? What issues and we have when we're going to fire commercial boilers? So the first thing we have to consider the fuel attributes for co-firing. And then we make the fuel profitable with additional attributes. This is second item is very important for a company because we have going through very complicated and costly process to make the fuel. And if we cannot make the profit, so the process is not going to be sustainable. So that's the key point. We have to make the fuel and profitable. So the next one is how we're going to validate this commercial and the pilot scales. So consider the few attributes for co-firing. So because we are going to co-fire in this case, in today's speech, we are going to co-fire in a pulverized coal boiler. So we have to consider not only the energy content, it's not eating BTU. It's not only about the renewable carbon, it's not about the boiler efficiency and so on. It's about the safety, the first thing. So ignition and flame propagation speed and stability. You have to burn that stably in the boiler. And the second thing, you cannot cause the coal boiler's corrosion increased. Okay, so you have to do not increase the corrosion, and you do not cause serious slagging. You do not cause flash, nice resistive changes, And also you do not cause, the ash deposit, the folding, and those issues. Okay, so looks like we'll only make a few that we get in to know the whole system, and beyond the field, only the field making, we have to consider the application characteristics. So that's why now we get to the field. That's suppose we only need to do this. Now we added the task, consider what's going to affect on the combustion, and what's going to cause operations of folding, corrosion, heat transfer, and what is going to cause the poisoning the SCR catalyst. We're going to poison and block the SCR catalyst or not, and what is the effect on the dust removal and the folding, kicking, corrosion, and ash resistivity. And if there's some bottom ash, then bottom ash cannot become a hazardous, okay? And the bottom ash cannot be, contains a higher carbon content that can be beneficially usable. So, and what is a fly ash is you have to pass through the TCLP test. You have to, and can be used. If there's a wet flue gas desulfurization, so you cannot affect the calcium solubility. You cannot increase the chlorine concentration. You cannot cause additional waste disposability issues. And such on, so we make a few, we have considered the whole effect on the system. So that's what talking the field. Okay, so this is a TGA measurement everybody's very familiar with. So that's a TGA. See, the 100% coal looks like much harder to combust in the 100% wood or biomass and the plastic. And you may say, okay, yeah, coal is hard to burn, wood is easier. But I think, if you biomass, if you think the fuel will combust fast and efficiently, I really suggest you to think again, because look at this table. Okay, so the coal has a 65 microns for the polarized coal boilers. The biomass economically we can make that into a 1,000 microns, and we consider that the density differences. We consider the initial fixed carbon content differences, and then we calculate for each particle. There's the char content is very different as a ratio. So the biomass has 210 times the charcoal content in the coal. So because everybody knows the char combustion is a controlling step. So that makes actually biomass is hard to burn than coal. Okay, if you consider the space and time in the boiler. So another thing is that the volatile rich. So because the organic waste and the lack of wood biomass has over 70–80% of volatiles, and coal probably only 30–40%. So we think the biomass is very easy to burn. But when we put this fuel into the polarized coal boilers, you get a plume and the smoke. So the volatiles goes very fast, like the earth flue gas stream to the superheater section. So you cause the superheater slugging, and that you damage the downstream equipment. So that's the first issue. And the second issue, when you inject the fuel into the burner near the wall, the fuel starts ignited and burn. And if you do not control the injection speed and carefully, really cause the burner damage and the incomplete combustion and the slugging issues. Okay, the second thing is the particle size. If the particle size is too big, So when the particle is injected by from the burner, so where the momentum is bigger, so that large particle will keep moving toward the wall and will hit the wall. So particle hit the wall and lost the inertia, and so that will fall down from the burner. So that's from the bottom edge. So it's without fully combusted. On the power plant in the site, I personally see a lot of those the sawdust and the materials in the bottom edge. So that's you cannot burn that large particles. And if the particle is small and it has the issue that they escape to the upward and the burning on the superheated sections. So that is going to damage the superheater section as well. So the particle cannot be too small, cannot be too big. So now we have the particle size issue on the reaction boiler efficiency effect here. And if it's too small, your operator is not safe. If your particle size is too big and you cannot complete combust the material. So give us a small window between. You have to size the materials based on your operation and the property. In this region, you can achieve safe operation and increase the boiler efficiency. The efficiency negative is increased because the axis is a reduction in the boiler efficiency, okay? Now we can see this, and another issue is that you have that thing controlled, you still have an issue. You have to control your injection speed and faster than the flame propagation velocity. And this is the pictures I took on site. On the left side one, you can see the plume over there. That is not ignited. That is perfect. Okay, so you inject the fuel into the boiler. They will ignite a little bit far away from the wall, from the burner, and then the flame push forward. It's not backward. And the middle one is you ignite it near the burner, But this is still okay because of the flame push forward. And the right one, that's dangerous. This is really, really dangerous. The flame burning and going to near the wall, and we will pull back. Okay, so this is an issue. So we have to control the fuel gas velocity and the flame velocity. Okay, so we get those things understand, so we will make a fuel profitable with the additional attributes. If we only sell the customer with a fuel, with the renewable energy, with the heating value, we are not going to make a profit because our process is too complicated and cause a lot of costs involved. So we have to make the fuel into something valuable and as valuable. So what are we going to do? We're going to add the additives into the fuel. Using the fuel as a carrier, to bring some additional benefit to the customer. So now this is the way we're going to. Okay, so we'll go to the customer side. So what are your issues? You have emission control. Okay, we add the sorbents into the fuel to control your CO2 and SO2, not CO2, SO2 emissions. But if you burn lignite or you burn a lower fusion temperature fuel, we can add something to raise your fusion temperature, and so on, so on, so on. So we, according to the requirements for the customer, and we can add modulate the fuel. So we can finally make a profit, and not only by the energy content, we make the fuel by selling another attribute. Okay, so we make tons of fuels, and we commissioned over 2-3 years pilot testing program, and this boiler is have a 300,000 BTU per hour of heat input, and we commissioned a very, very comprehensive test. We monitor the acid gas reductions, and we investigate how our fuel going to impact on slugging, falling, and the ash resistivity, and the high temperature, low temperature corrosion, and boiler efficiency. And how that going to affect the particular metals emission, and how the trace metals and the dioxins and so on. Okay, so somebody may say, okay, why you make sense so complicated? You would just simply blending the polymer fibers with a core. Okay, and I'm telling you this is not going to work because that's what exactly that we did. We blend 10% and the 20% of fuel without pelletizing, without adding the sorbent. And you can see the flue gas temperature continuously rises up, and eventually the slugging and the folding happens and downstream, and you have to stop the operation. So that's what you cannot do this way. And using our method, you can see we can add it, and the SO2 emissions from probably about 1600 ppm down to about 300, 400 ppm. Depends on the sorbent amount. And the draft fan is pressure runs pretty smooth and stably. So we do not have that issues anymore. Okay, so this we do generate some dust on the superheaters, but this superheater is very loose, and you hit and the dust goes away. So that means during the process we can use a blower to clean up heat transfer surfaces. See, this is a pretty good video. You see that? See, go away. Okay, good. Okay, let's move on. Okay, so and the next thing is that why you put the sorbent or the additive into the fuel, why you do not blend that fuel sorbent with the fuel directly. Okay, I'm telling you this is not going to work either because this is a way. And if we coal and the sorbent simply blend, and you can only achieve about 20–30% of sulfur reduction. So that's because at over 1300, 1600 Celsius temperature, that's whatever sorbent is going to be centered, and it's not going to work. Okay, and if we use a single sorbent and inside the fuel, we mix the pellets and then pulverize, that can increase the generation of power SO2 removal efficiency up to 40%. And if we use a hybrid sorbent, and we can increase the SO2 reduction efficiency over to 90%. But remember, this is achieved under 1300 to 1600 Celsius temperature. And the pellet test results for other parameters against components. So you can see basically we can reduce almost those things we measured, like the mercury and the non-methanol organic compounds and the dioxins, furans, HCl, HF, and all those BTX. Okay. And importantly, our testing results meets the requirement of USEP's boiler match rule and the boiler's MACT rule, and says the maximum achievable control technology limits. So we can meet the boiler's environmental requirement. And next we move to the commercial demonstration. The host utility a 125 megawatts tangentially fired polarized coal boiler with a no nitrogen burner with a closed loop overfire secondary air. So we has a ESIP for the PM control. And so this is a testing site when we conduct a test over there. And the commercial demonstration results is also confirms also very nice results with the SO2 reduction over 90%, sulfur-3 and all those things. It's very good. And the plus fly ash LOI and unburned carbon reduced by about 50–70%. And the ash is still past the TCLP analysis, and is still usable and can be beneficially usable. And there's before the commission of the commercial test, there's a big concern. Our fuel is going to cause the corrosion for the boiler. To validate the purpose, we hired a consulting company to put the full probes in the high temperature in the boiler section, and in the another in the superheater section, and the water wall corrosions and the downstream of the total 4 positions with the electrochemical sensor online real time to measure the corrosion. So our results confirmed basically there's no increase in corrosion. And in contrast, we actually reduced the corrosion a lot for some parts. Some parts it did not increase. It's negligible means there's no negligible corrosion. It's not our results negligible. Okay. Okay, so that's basically close my presentation. I want to address 4 remarks. The number 1 is the solid organic waste can be converted into a fuel useful for energy production with additional beneficial attributes, and depends on what's the requirement. And second one, when you do this, you have to understand the differences between the waste and the coal, physically and chemically. This is very, very important. And the third remark is understand the characteristic of the combustion system, not only about the combustion. And engineering the fuel accordingly is the key to success. And the last one, and the transforming basic knowledge, especially I want to speak to the young colleagues today. Transforming your basic knowledge into practice requires consideration of temporal and spatial variations on the site. Thank you very much for your attention.
Thank you very much, Professor Bai, for your nice presentation. I think the waste derived fuel is worldwide problem, right? And you share the idea to us about the process that I think is very useful for worldwide. And since we have quite limited time, Professor, so maybe I will leave your contact information in the chat box, just in case that the participants would like to ask you more information about the process of coal firing with the coal. Thank you very much, Professor.
Thank you very much.
Yes. Okay, our next speaker, Ms. Tan Kan Trin Lee from Thammasat University.
Do you see my green card?
Yes, maybe I introduce you first, and you have about 10 minutes for the question and answer, including your presentation, okay? So try to keep on time. Okay, let's start.
Yeah, thank you so much. Hello everyone, my name is Tan Kan Trin Lee. I'm a master student of Thammasat University. Today I'm here to present about reparation of bimetallic cobalt copper supported on activated carbon for selective oxidation of 5-HMF. My presentation includes introduction, experiment, result, and conclusion. Now let's begin with introduction. Firstly, I would like to introduce about XMF. XMF is renewable resources of lignocellulosic biomass. It's derived from glucose and fructose by isomerization and dehydration. XMF is a life form for converting into useful compounds such as levulinic acid and DMF. XMF derivatives have many applications such as polyester or refuel. Next, I would like to talk about FDCA. FDCA is identified as one of the shale bioenergy value-added chemical robot by U.S. Department of Energy. FDCA have many advantages. The more important application is can be used as the polymer monomer for production of biopolymer. For instance, FDCA have the similar structure with terephthalic acid, so PEF derived from FDCA is not only an alternative to petroleum based PET, but also it has some better property than PET. This figure shows the oxidation of HMF to FDCA through two different pathways with DFF and HMFCA as intermediate agent. In my research, I want to introduce about the conversion from HMF to FDCA with the supported bimetallic cobalt copper supported or activated carbon catalyst and hydrogen peroxide as oxygen source. Therefore, in my research, I want to focus two things. Firstly, is the study effect cobalt copper and the physical characterization of catalyst, and after that, application catalyst in FDCA production for HMF oxidation with different conditions, such as time, temperature, ratio of HMF and catalyst. Next part is experiment. There are three steps in the catalyst synthesis. The first step is wet impregnation between two nitrate salts with the activated carbon. The second step is calcination. And finally, before apply catalyst in the HMF oxidation, the catalyst needs to change from the metal side by reduction on the hydrogen gas. The catalyst is also checked physical chemical characterization by nitrogen sorption and XRF. About the application catalyst in HMF oxidation reaction, the experiment is performed in high-pressure autoclave with the appropriate time and temperature. In the end of the reaction, the liquid product is analyzed by HPLC in order to calculate HMF conversion, FDCA yield, and selectivity. Because my research is still in progress, so this is some result I have of the study. Firstly, about catalyst characterization. This table shows the result of elemental analysis of catalyst in 4 different ratios of cobalt and copper. Almost the percentage belong to the cobalt and copper. However, it's still about 3% belong to other metals such as phosphor, silic, and calcium. The next table shows the property of catalyst in 4 different ratios of cobalt and copper from nitrogen sorption characterization. When the ratio of cobalt increase, it leads to the mesopore sulfate decrease and the microbore sulfate increase. I think that when more cobalt added, the metal attack to the mesopore first, and currently it's also react more microbore. That's why the surface area and pore volume of microbore increase when increase the ratio of cobalt. This figure shows the nitrogen sorption isotherm and bauxite distribution. We can see that all the sample can belong to the isotherm of trifor with historic look of X4 indicating mesopores of the different size. I also apply catalyst in the HMF oxidation in order to find the best activity of catalyst in the reaction. This figure shows the HMF conversion, FDCA yield, and selectivity between no catalyst and when apply the catalyst. Firstly, we can see that HMF conversion nearly 100% is demonstrated that hydrogen peroxide support rich oxygen source. Besides that, when apply the catalyst in the HMF oxidation, the FDCA yield react more than 20%. Moreover, for cobalt copper supported activated carbon in the more efficient catalyst in the HMF oxidation with the FDCA yield higher, nearly 40%. In the final pass conclusion, Firstly, I want to conclude that bimetallic cobalt copper supported on activated carbon have the isoform of tri4 with history loop of X4. Besides that, when ratio cobalt increase, it leads to mesoborsulfate decrease and microborsulfate increase. Moreover, when apply the catalyst in the XMF oxidation, we have the XMF conversion high, nearly 100%, and higher FDCA yield belong to 4 cobalt copper supported on activated carbon catalyst, nearly 40%. I want to thank you, my advisor, Professor Chanatip Sama and Biochemistry group. That's all my presentation, and thank you for listening.
Thank you for your presentation. Are there any questions from the participants and committee?
Okay.
We still have time.
Okay. So thank you very much for your presentation. And Mr. Tring, so I have a quick question for you. So could you explain for us why the conversion of HMF nearly 100%, but the percent selectivity of your FDCA only 40%, nearly 40%?
Yes, Cara, thank you your question. Because trend for the conversion from the XMF to the FDCA is need to transfer first XMFCA and DFF, and they are the intermediate agent before the conversion into the FDCA. However, the conversion from XMF to XMFCA at the lowest step, so almost the percentage 60% belong to DFF. Another survey of another paper that show in the quick product is have the DFF, XMFCA, and FDCA.
Okay, so could you determine your byproduct in your reaction?
Yes. Yes. It's have the I will check by free CMS, but because my research is still in progress, so after that I will continue by check by CMS.
Thank you so much.
Excuse me, I have
Yes.
one question.
Yes,
Short question.
Yes.
Thank you for the very nice talk. And I have a question about the utilization of hydrogen peroxide. So do you need a stoichiometric amount of H2O2 or excess amount of H2O2?
Your question is mean that why I choose the hydrogen peroxide in the reaction, right? Sorry. Right?
No, Professor argue about the percent of hydrogen peroxide is in stoichiometric or excess amount.
Oh, excess. Oh, so
No. I try to explain her.
So sometimes non-productive consumption of hydrogen peroxide will occur using the metal catalyst.
Sorry. All right. Oh.
Okay.
Sorry. I use the hydrogen peroxide amount, a set amount. I use the 10% with the 10% with the XMF amount of XMF.
Okay, 10%. Okay, thank you.
Thank you so much.
Okay, thank you very much. It's about the time for the next speaker. Nice presentation. Thanks, Finley, for your presentation. Okay, our next speaker is Mr. Lee Kim Hong Pham from Thammasat University. Pham, would you please share your slide?
Okay. Sorry, can you see my slide?
Yes, clear slide. Okay, you can start now.
Okay, thank you very much for your introduction. Good afternoon, everybody. My name is Lee Kim Hong Pham. I am a PhD student from Thammasat University. Today, I'm glad to share with you about my work done before we ask my topic of the preparation of the solid nickel profile support on nitrogen dumping active carbon and application for hydrogenation of the palm kernel cell. For the motivation of the biomass resources I'm using for the abundant energy available in Thailand, in this case, I'm using the byproduct from the palm oil tree. In this case, you can see that the oil extraction from plant and kernel have some lot of the restore cell. It's named a palm kernel cell. From that one, it can be to convert to fuel via the pyrolysis. However, the pyrolysis oil we cannot apply directly to a commercial fuel due to a lot of the oxygenate compound, with stagnation from the hemicellulose and lignin is the main component of the lignocellulosic of biomass. In recently, hydrogen treatment have been attractive due to hydrogen can deal with a lot of the oxygenate to convert from oxygenate to hydrocarbon. For the catalyst, we have two types, two components using a metallic catalyst. Is this the catalyst, the metallic active site using the plate role for reactive of hydrogen, and moreover for acid catalyst support using for breaking to increase dispersion and also have an acid side for reactive for carbon oxygen bond for creation. Further review, most of the catalysts have best efficiency for deoxygenation using the mobile metal-based catalyst or bimetallic sulfide catalyst. Even its high conversion and high deoxygenation, but it's very high cost due to the mobile metal and easy deactivation or adding the sulfur in the core feeding. So it very disadvantage when can application in the real one. And from that one, the motivation I would like to development for change about the motor metal like platinum like to transition metal like nickel. In this case, I using nickel phosphide. It's a modified test of the nickel. We have a similar to the property of a noble metal, but it's cheaper than. The second one, I also development about the support material using the utilization of the carbon source. It's a restore of the pyrolysis of the biomass. However, the challenge from compile two components is not easy due to its low activity and also a diversion of the metal nanoparticle. From that one, I development to modify the activated carbon, first for utilize of the carbon and also for improvement for carbon property using a nitrogen in a carbon nitride matrix is helpful to improvement for the dispersion of the nickel phosphide and also recocking and also chip material. From that one, the objective of my work, I study for preparation of nickel phosphide support on nitrogen doping activated carbon, and as well as study about physical chemical characteristics of the catalyst, and then the application when we hydrogenation of the palm kernel cell under the mild condition like atmospheric of the hydrogen gas, low metal, low catalytic lock-in electron, only 10% to the biomass weight. For experimental, the carbon view from the commercial one before we doping with nitrogen will pre-oxidation with the nitric acid, and then we'll mix with a host of a melamine with different ratio in my study in calcination at 900 to form the nitrogen dominated carbon. After that, the carbon bed includes the pure activated carbon for comparison with the modified activated carbon. Will West coordinated with the nitrogen and phosphorus by coordination method and calcination in hydro reduction is 600 to 2 hours to form the fresh catalyst. The fresh catalyst filter will characterization to determine about the catalyst property like crystalline porosity, surface, chemical state, or acidity or reductivity. Finally, we application in a mild condition in my case using integrated catalytic hydrogenation of the palm kernel cell. In this case, I using the low catalyst lock-in just only 10% to biomass, and the condition in study under the atmospheric pressure of the hydrogen and the low and not high much temperature at just only 350 degrees Celsius. So oil will collect and separation and filter for characterized by VCMS. Let's talk with a result discussion. The first one, I would like to talk about the morphology and textual of property of the catalyst. In this case, for the nitrogen desorption substance, if present a type for which the hydrolysis H3 present the mesoporous of the material. After the nitrogen doubling, we can observe that the low amount of the nitrogen absorption is green. The reason is we have some engage of the metal on the surface and also in the pores. The reason why the surface area decrease and also mesopore is decrease. And for about the morphology, we observe that the dark color is a metal side and the black one is a metal line, sorry, and the dark is belong to the carbon nitride which produce obtained from the calcination of melamine. And we can observe that when we see the TEM image, we can see that have a strong interaction between the metal and the support material. XRD also study, and we can see in this slide, we can from that one, without the nitrogen doping to present strongly the Ni2B, the one phase of the nickel phosphide. However, when we doping with nitrogen, the it's avoid to form formation of the another phase of the nickel phosphide like Ni3P5 and degree helpful to degree about the crystalline of Ni2B. For the more information, I study by X-ray for photoelectron in this case. In this slide, we see that nickel and phosphorus and Ni2B present in binding nitrogen in here. And interestingly, when we doping with the nitrogen, we have some interaction between some support and metal. For example, for 25% in comparison without the nickel, we can see that so on the binding energy of the nickel will shift to higher energy. That's the reason why the reason is the interaction between the nickel with the support material. For the reducibility and acidity also study in this slide. In this case, we can see that without the nitrogen doping reason just for by reduction of the nickel oxide and the nickel phosphide. However, every doping with the nitrogen, we observe the new bit like bit number 5 and 6. It belongs to reduction of the hybrid of the nickel, carbon, and nitrogen. However, when we higher the melamine doping, we also refer to for deal of the carbon. Rapid carbon is present in a big number 7. Interestingly, when we doping with nitrogen, we also improvement about the acidity is shown in this slide. The reason is when we have a lot higher of the nitrogen level, it also can come interaction and higher metal and phosphorus locked in. It's reason why even nitrogen have a best property, but the acidity of the material will increase due to the higher of the metal locked in. And last one, I would like to talk about the applications in the pyrolysis. In this case, we can see that we have a three main product by pyrolysis product. And with the nitrogen doping, we observe that the fraction of the gas product we higher than comparison with nitrogen without doping and no catalyst. It reason the acidity of the Ni2B support on nitrogen doping acid carbon higher acidity. In the chemical composition of pine oil, we observe that the oxygenated compound without catalyst, its main composition belong to alkoxyphenol. After application in the catalytic, we observe that without the nitrogen doping refer to form from the alkyphenol and also higher aromatic hydrocarbon and also aliphatic hydrocarbon. Interestingly, whenever nitrogen doping is very preferred to form the selectivity to higher alkyphenol, and we can observe in the thicker B. And in the notice that the all my process with under the my condition and only the by catalyst locked in just only 10% to a biomass weight. And finally, I conclusion from that one, I found that we can modify the activated carbon to boost the support material. And under the my condition, we also to high selective to form alkyphenol from the waste material. And finally, I would like to thank Thammasat University, our lab to Belgium laboratory and also organizer of the conference. Thank you very much for your listening.
Thank you very much, Pham, for your presentation. Okay, it is time for open for the question. One question is why the liquid product is more than when there is no catalyst used? Okay, one from participants, could you explain?
The liquid product, when we application with the catalyst operating the solid product is include the biochar and coke. In this case, it's nearly same, but we have a competitive fraction of the liquid and the gas product. The reason is when we application of the catalyst, we have some filter operating for the deoxygenation or cracking. So the last molecule to convert to be a lighter one. And so the reason is a fraction of the liquid product will decrease when application with the catalytic.
Okay, thank you, Pham. Are there any more questions from the committee?
Okay, so thank you very much for your presentation. I have a short question for you. So I didn't say that you mentioned that how long the reaction take and how can we make sure that the biomass would completely pyrolyze in the pyrolysis zones. Could you explain?
Okay, for that one, I just talk about that one a bit about experimental. Biomass in this case, we will keep in the biomass hopper in here. Before we reaction, we optimize already about the temperature, about the reaction time, and also about the biomass fitting with the time. In this case, how we make sure about that the biomass, we first thing I calculation about the biomass fitting, and after reaction, we can also that the biomass still come friction, still remain in that still remain in the fitting zone or not. And the second thing, how we can know about the biomass will completely to variation. The solid product can be a biochar is a product of the pyrolysis of biomass is observed in here. After reaction, we can variation about the time like 10 20 or something, we observe that about like 1 year. If if follow the time, so the mass of the product is similar, we cannot record such the time for reaction to completely for convert biomass in the parasitic zone.
Okay, one last question from the participants. Why did you select pyrolysis temperature at 550 degrees Celsius? And what kind of the gas product?
Okay, for the temperature, I choose 550 is one optimized temperature. For which temperature will produce a last gas, highest liquid yield. In last study, I'm sorry, I'm not showing here, but for my first study, I studied from 450 up to 600, and I observed that as 550 will will produce high yield of the liquid yield. And about the gas product, because for my topic still progress, so some of the gas product I will filter for analyze due to for replication. Yes.
Okay, thank you very much. It's about the time. So if you have more questions to Ms. Lee Kim Hong Pham, you can send direct message to him and he will be like standby for answer your question. Thank you very much, Pham.
Thank you, Pham.
Okay, our next speaker is Mr. Lukman Abdullani Sani. Are you there from Shenyang University of Chemical Technology? Okay, so you have two presentation, right? First one is effect of yttrium addition and another one is effect of combustion temperature. So if you are ready, you can present now.
Good morning, good afternoon to, depending on our different time zone, to our highly respected professors, associate professors, teachers, and my fellow students. Well, my work is on methanation of carbon dioxide, which I use YB to promote the nickel alumina catalyst.
Please, yeah, turn over.
Hello? Can you hear me?
Yes.
Okay. The title of my work is Effect of YB addition on nickel alumina catalyst prepared by solution combustion for the methanation of carbon dioxide. And we can see from my table of content, this is what we'll be discussing. I think I'll be your speaker for the next 20 minutes. So my introduction, we talk about climate change. Well, climate change has posed a great threat to our planet Earth due to the global warming, which is caused by the release of greenhouse gases. Now, these greenhouse gases, most of the greenhouse gases is carbon dioxide, which is mainly due to the biogenic and anthropogenic source. So what can we do now is to find a way to utilize this excess carbon dioxide in the atmosphere. So this brings us to CO2 utilization. Now, when you talk about CO2 utilization, it means ways we can find to utilize the excess carbon dioxide in the atmosphere. And one of the method is the CO2 methanation. Under the CO2 methanation, the main the main component of the CO2 methanation is the conversion of CO2 to methane through hydrogenation. Now, the main component, the main factor in converting the CO2 to methane is the catalyst. The catalyst consists of the active metal and the support. Under the active metal, we talk about elements like PT, PD, Ru, RH, and nickel. Most of the first of 4 to 5 elements that I mentioned are quite expensive, which leads us to the nickel catalyst. Now, the nickel catalyst has been used widely and is more cheaper and available. However, at a certain temperature, at about 358 degrees Celsius, the nickel loses its property of ferromagnetism and become paramagnetism, which is an ability of an element to become tiny magnets and attract to each other, as you can see. This is caused due to the elements in the outer shell becoming highly paramagnetic. On the other side, we have an element YB, which is called ytterbium, which is the least paramagnetic of all the rare earth elements. This is due to the enhancement of the magnetic field caused by the alignment of the magnetic dipole is relatively small compared with the applied field. Now, if we have an element that has least paramagnetic property, and we can be able to modify the nickel alumina catalyst, we believe that we will be able to achieve a stable catalyst at the temperature that the nickel becomes paramagnetic. And this is what the work is all about. So in the process of synthesizing the catalyst, we selected the solution combustion method, which is due to the fact that a lot of the method of making the catalyst, for example, the impregnation, the precipitation, the sol gel, all shows the solution combustion synthesis have shown to have better performance. So we decided to use the solution combustion to synthesize it. However, these are the components of the solution combustion. You have the oxidizer, the fuel, and the solvent. And we were able to select the citric acid as our fuel. And then the solvent, we use ethanol. And then we have the oxidizer, the nitrate, as the nickel precursor. So this is the catalyst synthesis method. We synthesized the pure nickel alumina, and then we promoted it with 2%, 4%, and 6% YB, as you can see on my screen. So these are the components, and we were able to synthesize the 4 types of catalyst. And this is the mixture, how we were able to mix it. And then this is the temperature distribution in a mouthful furnace. As you can see, from C1 to T0, we heat it to C2, T1, which is the combustion temperature. And then we heat it again to the calcination temperature. And then from there it stops, and we allow it to cool down back to C4, T5, which is the end temperature. From there, we started to characterize our catalyst. As you can see, we did the N2 absorption desorption. You can see with the addition of the YB 2%, 4%, and 6%, all the 4 displayed type 4 isotherm. However, the hysteresis were different. The nickel alumina showed H1 hysteresis, while the promoted 3 catalysts gave H2 hysteresis. And the H2 hysteresis is related to smaller pore diameter of the catalyst. As you can see from the pore diameter in the figure B, the pore size was smaller. And then in order to understand the interlayer structure, we did the FTIR analysis, which gave us the breakdown of the component, the structure in it. And then we go further to calculate the surface area, the pore volume, and the pore size from the absorption desorption isotherm. As you can see, as we started to add the YB, the surface area increased. However, the best combination we had of the surface area, pore volume, and the pore size was with 4%, and an increase above the 4% shows to the pore size start to increase again. So the SCN image also shows that as we started to increase the YB promotion, the 4% shows smaller particles, while more increase of the YB started to accumulate. We went ahead to characterize the XRD patterns, which shows that this is the A part was before reduction and the B part was after reduction. On the A part, you can see the nickel oxide is more dispersed, which also went ahead on the P part to show that the nickel and the reduced nickel is also more dispersed compared to the pure nickel alumina. However, when we above 4% shows that the beginning of accumulation of the nickel. And then the TEM image also confirm what we saw on the XRD, which shows the smaller particles of the nickel. On the 4% is higher. So we also calculated the average particle size on the 4 catalysts, and you can see the average particle size on the 4% is also lower compared to the remaining. And the XPS pattern shows us that when we started to add the YB, when we started to add the YB progressively, at about the binding energy of 198, the YB peak shows to be at YB in oxide form, which is not more reactive than the ions. Mostly, generally, the peaks before the 200 YB in form of ions, which is more reactive. But in the 6%, we don't have the YB in form of ion. It's only in oxide form. And the Ni2P spectra also shows that the 4%, as we add the YB, the nickel oxide is more reduced. But after the 4%, the nickel oxide peak also reappeared. We went ahead to, if you look at the oxygen spectra, there's O1s, you see that the oxygen vacancy increased with the increase of the YB up to 4%. We were able to calculate the oxygen vacancy. The 0 II represent the oxygen on the surface, while the OI represent the oxygen absorbed on the catalyst. And you can see the 4% was higher, and above that we start to receive a lower amount of oxygen vacancy. And we went ahead to this shows us the H2 TPR, the CO2 TPD, and the H2 TPD. On the H2 TPR, you can see the 4% shows the peak. The peak on the 4% is more of the alpha. We have the alpha, the beta, and the gamma. The alpha is the more reducible nickel, which serves in increasing the activity of the catalyst. So as we started to add the YB, the peak on the alpha was increasing. However, after the 4%, the peak of the gamma started to increase more. So we went ahead to do the CO2 TPD, which also gave us almost a similar result of the 4%, which is give us the higher CO2 absorption. And then the area under the H2 TPD also the same. We have more desorption of the hydrogen on the 4% catalyst. This is the breakdown of the total reducibility of the catalyst. As you can see, on the pure nickel alumina, we have 0.82. On the 2%, we have 1.16. On the 4%, we have 1.35. And on the 6%, we have 0.87. Also confirming that the 4% is much higher. We analyzed the CO2 TPD also and calculated the basic site density also. And you can see the 4% is also still, we have 33.3, which is more higher than the pure nickel alumina, the 2%. However, above the 4% shows to decline in the CO2 absorption, the hydrogen absorption, and also even the reducibility of the catalyst. This is the H2 TPD, which is what I just explained. We calculated the area under the curve. As you can see, on the 4% is much higher. So after we have all this, we now ready to carry out the methanation reaction. This is the operating condition we used. They used a catalyst of 0.5 gram GHSV within this range, and the temperature was set between 200 to 500. The pressure range was between the atmospheric pressure, which is 0.1, and then the 2 megapascal. This is my apparatus that I used in the reaction. This is the arrangement of the reactor. I have my N2, H2, and CO2 gas pass through the reactor. And here I have my catalyst set here with support with the pass wool and pass hand under it. Which after I collected my gas and then I tested it in the GC apparatus. So the result shows that as we increase the YB concentration, the CO2 conversion increased. However, after the 4%, we saw a decline of the conversion. Also, the selectivity was higher, and even the CH4 yield was also higher on the 4%. And then we carried out also different tests like the GHSV, the different feed ratio, and then the pressure test, which due to the time limit, I tried. % was better than the 6, and then the pure alumina nickel. So we decided that, okay, from this moment, go back.
Excuse me, Lukman, you have about 2 minutes for presentation for your time slot of
2 minutes?
Presentation. Yeah, 2 minutes, because
okay.
You wrap up. Could you please wrap up all of the work?
Okay.
Thank you.
So we did the stability test and to compare the 4% and then just the pure nickel alumina, and also the 4% shows the higher, very high stability as we thought. And then we did the TG of the used catalyst after the reaction, and we observed that the pure nickel shows sintering of the nickel, while the promoted shows more dispersed and there was any carbon deposit on it. The TG confirmed there was carbon deposit on the pure nickel alumina. So this is generally, in conclusion, we were able to say that the addition of the YB was able to stabilize the nickel at a very high temperature, but excess amount of the YB could be detrimental to the activity. This is, and we were able to confirm this from the reaction, and then the thermal expansion of this element shows that the YB is almost twice that of the nickel, which confirms our observation and concluded our result. So generally, this is the summary of everything. We can say that the YB increased the basicity of the catalyst, increased the reducibility of the catalyst, and was able to increase the activity and stability of the catalyst at high temperature. Thank you. I think this is...
Thank you very much for your presentation. Okay, so we still have time for question and answer. Are there any questions for the participants or the committee?
I think I have the second presentation, right?
You wrap up for 2 works within 20 minutes, right?
You said?
Yeah, it is take 20 minutes already for because you have two presentation, but you take 20 minutes. So it's
okay.
Time is gone.
Okay.
Yeah, so or you have the second presentation as well, right? Could you summarize to the end of the second presentation?
Okay, I can summarize it.
Yeah, please summarize the second one. No need for the interaction because it's the same reaction, right?
Yes.
And the same catalyst also.
Okay. I can summarize it in a few minutes.
Yes, the second one. Yeah, please summarize it.
Yes. Okay, the second work was about the solution combustion method. Well, the solution combustion method we use, we realize that there are factors that can affect the solution combustion method itself. The type of the fuel used, the solvent, and the combustion temperature. So in this work, we were just able to concentrate on the combustion temperature of the catalyst, which we synthesized different nickel alumina catalysts at different temperature. The first one was at we used the impregnation method, so we just heat it to 100 degrees. And then the other one, we did the combustion temperature at 350 and then 500 and 700 degrees. It was also almost the same. So,
yes, please go to the summary that what you found for this second work.
What we found was as we increased the temperature, the oxygen vacancy was reducing, and the nickel oxide was also increasing. So we were able to understood that the nickel alumina synthesized at 350 degrees was the best temperature for synthesizing the catalyst.
Mm-hmm.
Yes.
Okay, thank you very much for the presentation. So since the time limited, are there any short questions from the participants? By the way, you still online, right? For standby for further question from the participants. So one question. Okay, could you explain why yttrium promoter be helpful to stability of the nickel? Okay, one question, please.
Okay, yeah, as I explained earlier, the YB is the least paramagnetic of all the rare earth elements. And this is a property it has within itself. So the nickel at about high temperature becomes paramagnetic. Now, having an element that is least paramagnetic into an element that at high temperature that is highly paramagnetic, we believe that the element could absorb or reduce or negate the paramagnetic effect at that point. So that was what why we decided to use the YB, and it works in our favor.
Okay, Thank you very much for your answer and nice presentation. Okay, thank you very much. That is the end of the first session. The next session, actually the schedule will be the refreshment, but we are about to delay about 20 minutes already. So I think we better start the second session. The chairman will be Associate Professor Chanatip Samat from Thammasat University and Dr. Suchada Siri Sombunchai from Nagoya University as a co-chairman. Okay, let's start the second session.
Good afternoon, everyone. Can you hear me? Hello, can you hear me?
Yes.
Okay, so good afternoon, everyone. Let me start the second session of YSCRC 2021. My name is Chanatip Samat from Thammasat University. I'm a chairman of this session. And Dr. Suchada Siri Sombunchai, she will serve as a co-chairman of this session. This session consists of 2 invited speakers and 6 oral contributions. So the first speaker is an invited speaker from Japan, Professor Kao King Kwon from Hirosaki University. Let me to introduce Professor Kao King Kwon briefly. Professor Kwon graduated from a bachelor degree from Sichuan University, and after that he going to study the master degree and PhD in Sichuan University in China. And after that, he also got the second PhD at the Kyushu University in Japan. After that, he going to the postdoc in Germany and also Fukuoka University. Fukuoka Women University in Japan. And after that, he get the position in project assistant professor at the University of Tokyo. And also in 2010, he moved to Hirosaki University and worked as associate professor at the North Japan Research Institute for Sustainable Energy. And in 2016, he got the promotion to be the full professor at the Institute of Regional Innovation, Hirosaki University. Professor Kwon get many awards, such as the Frontier Award from the Society Chemical Engineering Japan, and also from Hirosaki University. And he published many papers, more than 250 journal paper. And also he got over 5,000 citations from the other researchers. So today he will present in the title Development of Small Scale Biomass Gasification System. Please welcome Professor Kwon.
Oh, wait a moment. I can't find my file.
Okay, got it. I can see your screen now. Okay.
Okay, now it's okay.
Yes, okay.
Okay, thank you for your kind introduction. Also, I would like to thank Professor Swadi and all others in Thammasat University to organize this conference. Here, I would like to introduce our recent research on the development of small-scale biomass gasification systems. So as you know, for the power generation from biomass, have these 2 ways. One is for the combustion, another is for gasification. For combustion, we always burn out the biomass and to get the heat and to produce the high pressure steam and use it to run the steam turbine to get the electricity. Another process is gasification. In this process, we use a limited oxygen or vapor, water vapor, to gasify the biomass to the fuel gases and use it to drive the gas engine or gas turbine to get the electricity. In this process, we can also use this fuel gas to drive the fuel cells to get electricity. For gas engine and the gas turbine or fuel cells, it have high conversion efficiency to get the electricity. On the other hand, in these two processes, for the steam turbine or the gas engine, gas turbine, or fuel cell, they also generate the heat. If we can co-generation of heat and power together, and the total system, the efficiency will be increased to some extent. So in general, when we develop the power generation system, we also consider how to use the waste heat in this process. When you check the Google or some literature, you can find in the world maybe about 200 kind of gas fuels in the world. Here I summarize the typical types of these kind of gas fuels. For the first three types is a fixed bed gas fuel. In general, for the small scale biomass gasification or coal gasification, we always use this kind of gas fuel. Another is a fluidized bed. You know, when you use a fluidized bed, you must crush the biomass to a small size. And in this case, you can increase the gasification efficiency. And another is, for example, the entrained flow. This for a large scale biomass gasification or coal gasification, we always use this kind of gas fuel. We also have some new type of gas fuel like the KBR transport gas fuel or dual fluidized bed gas fuel or triple fluidized gas fuel. But all these type gas fuel, they always operated at a large scale. In this case, they can increase the thermal efficiency, but the system always very complexity. Another technical requirements is also very high, so we should develop new some technology to improve the total power efficiency. But for the biomass, you know, it wide distributed on the Earth. When we collect the biomass, we should consume many other energies to do this work. So in this case, I think the smaller scale gas fuel is more suitable for the biomass gasification. So in our group, we try to develop some novel type small scale biomass gasification system. When we check the literature, we can find that the commercial small scale biomass gas fuel also have many types. This one example is this type of small scale biomass gas fuel is produced by World Power Labs. It's a USA company. This kind of gas fuel, it has capability about 20 kilowatt to maybe about 100 kilowatt. This type biomass gas fuel, they work like this. The biomass put in this tank. After that, they pass through a drying section. This section, they use the waste heat from the syngas and dry the biomass. After that, get into a downdraft fixed bed pyrolyzer. After that, this combust in this type biomass gas fuel must have part of the biomass be compressed to generate heat for the pyrolysis and the reduction process. And after the obtained syngas can get out from here. And here also have many waste heat and use this waste heat to dry. At the same time, this kind of biomass gas can also co-produce the biochar. So this is a very useful small-scale biomass gas field in the world. Another type of small-scale biomass gas field is developed by Finland company. There's a water. This company have sold many this kind of in Japan. In this system, they use the co-generation of the power and the heat together. In Japan, the typical type is about 40 kilowatt, can produce 40 kilowatt electricity and plus 100 kilowatt heat. The weight is only about 4,500 kilograms. It's very compact. In this system, because they consider how to use the waste heat together with the power generation. So if you see this figure, you can see have 3 stages to recover the heat. So they can get more heat from the gas field and let the total system, the thermal efficiency can increase to a great extent. So all these commercial biomass small scale gas field, they always use the fixed bed gas field. You know, the fixed bed gas field always have 2 kinds of designs. One is the updraft gas field is like this. In this case, is a general, but sometimes in the fuel gas, in the produced fuel gas, always contain a large amount of tar. So in order to reduce the tar content in the fuel gas, they always use this kind of fixed bed gas field. That's a downdraft gas field design. In this case, the air comes from about the middle of the gas field, and the combustion will occur in this area, and the generate heat and can be used for the pyrolysis and the drying. After the reduction, this part is very important for produce the syngas. So in general, in this case, the obtained fuel gas always contain a low content of tar. So in general, for the biomass gasification itself is very simple. It's only a partial oxidation process. It's a exothermic reaction. And another is steam reforming. This always used in many the gas field like this. However, the generated gas always have a low heat value. When we design a gas field, we should consider the heat value in the obtained fuel gas. The heat value should be over 4.6 mJ per cubic meters. This data is very important. If the obtained the fuel gas, the heat value over this, almost the whole gas engine can be working by it. Another problem is for small scale gas field, we should consider how to reduce the tar. For the gas engine, it requires this amount of tar in it. Of course, if low tar is the best, but generally we can't get a pure fuel gas. So in our group, we we do many basic experiments. So we consider use a tar-char separated gasification system. That's because for the biomass, if you put it in the gas field, it will be pyrolyzed at a relatively low temperature, about, for example, 300 degrees C. In this case, the tar will be generated. After that, in this case, if the tar contact with the remaining char, in this case, it's a benefit for the tar decomposition to the syngas. But on the other hand, if the tar contact with it, it will cover the char. It will hinder the char gasification. So if we wanted to avoid here and let the tar and the char can gasify more effectively. So we consider a kind of tar-char separated gasification system. Simply to see, for example, biomass introduced to a pyrolyzer at first. In this case, the biomass will change to the tar or some kind of gases phase, and the remaining char will be separated with the gas phase. After that, the tar can be separated, treated in a tar reformer. We can use the catalyst here and improve the syngas production. So in this case, the syngas can come from the different routes. After that, we can get more syngas. So we can use this syngas, for example, use that for the hydrogen station or for the power generation, or use it also can to produce some liquid fuels or some chemicals. These are photos of the small-scale gas field developed in our laboratory. It says about the length about 1.5 meter and the width about 1.2 meter and the height about 2.5 meter. Is very complex. So it contains the pyrolyzer, char gas field, and the combustor and the tar reformer. Maybe see this figure, you can see more clearly on the working mechanism of this kind of biomass gas field. The biomass will mix with the hot sand here and get into the pyrolyzer. And then the tar will go to upset and the tar reforming here, and the remaining char will go to this char gas field and the gas fed to the syngas. After that, the obtained syngas can introduce to the gas engine to generate the power. So for this gasification system, we consider to let the pyrolyzer to work at a temperature about 500 degrees C. And the tar reforming, here we also use some catalyst. The working temperature is about 650 degrees C. And for the char gas field, here the temperature is about 550 degrees C. And the remaining char, the combustion temperature is over the 1000 degrees C. You know, in this system, for the red one is an exothermic reaction, and for this part, and this part is the endothermic reaction. So we want to get a balance between these two kinds of reaction, let the heat have a good balance and to save the energy. When we use this amount of wood biomass feed into this system, the power generation ability is about 17 kilowatt with a cold gas efficiency of about 74%. Of course, now we are still modify this gasification system. We want to achieve this. This is a target. So we also do some survey on the small scale biomass gasification system commercials in China, Thailand, and Japan. This is for China. You can see in China always have a large power and the capacity is very high. And then the smallest one is also about 200 kilowatt. But our purpose is lower than 100 kilowatt. But now the commercial one in China is at least 200 kilowatt for the biomass gas field. But in Japan, also have many companies to develop such kind of small scale biomass gas field. In general is lower than 200 kilowatt. Of course, now I also visit some company, they always use the technology from the USA and European. So in our group, we want to develop a novel type and then a small scale gas field, which try to let it can be commercial. This in Thailand. Thailand, you can see in Thailand also have some company and the university also develop some small scale gas field like this. So that's where I want to give a conclusion to my talk. So we consider we develop a tar chalk separated type small scale gas field for the biomass, but more modification is still necessary, and we hope it can be achieved the federal target in the near future. We think that develop a small scale gas field is more important than large scale ones for the biomass energy application in the future. So more work is necessary in this area, we think. Okay, that's all. Thank you for your kind attention. This is the photo of our group in this year. Thank you.
Thank you, Professor Guan, for your presentation. Any question from participant? We still have time a bit, or short, maybe one short question.
Okay, Professor Guan, thank you very much.
My presentation.
Okay, actually this afternoon I'm in a large meeting, but I always keep online. And I think you talked about the small scale gasifier, and I would like to discuss with you the possibility to form a joint, like a joint venture, like this kind of business partners with you and also Thailand in South Asia, and to commercialize some small scale gasifiers. Actually, you know, from the engineering aspect and also from the experience of application, we actually have somehow good accumulations. Therefore, I wanted to somehow to deploy our technologies into South Asia. Meanwhile, by this application can promote the progress in academy, especially our colleagues like the Samat and the Symposium somehow, all those colleagues. How about the possibility? I think we can discuss, can talk about later is this.
Yeah, that's now some Japanese company also interesting for this technology, but you know, we use the fluidized bed here. And in this case, we should consider how to crush the biomass at first. That also need energy. So many companies think it's better to use the For example, the pellet or some chips of the biomass. So last time I also contacted you. If possible, I also can develop some like the downdraft gas.
Two-stage downdraft. Okay.
Yeah, that's more easy to commercialize, I think.
Okay, so Professor Guan, this is Ding Rong. Hello.
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 Please show your picture. This is Ding Rong Bai, Professor Bai.
Bai?
Yeah.
Which one? Which one?
Professor Bai Ding Rong.
Uh-huh.
Yeah. So now he shows his. He's showing his picture. Yeah.
Which one? Which one?
Bai Ding Rong.
Bai Lao Si. Okay.
Okay. Okay. I got one question here. I got one question here, and Professor Guan, what's your view? What's your view, or what's your perception, regarding commercializing or large scale implementation of this small scale? This idea is fantastic. There's no question about this. It's a distributed energy, and then you talk about all the advantages. But what's the barrier, in your view, to prevent this technology from being commercially implemented? And schematically, that this looks great. But if we consider the few characteristics for the biomass, particularly, you have the chlorine content, which becomes a serious issue. And the corrosions, if you burn in the gas engine, and you have to get that stuff clean, because the gas engine runs a pretty high temperature, right? And there's also alkali metals, like the potassium or those things, and that's going to is an issue as well. And not mention about the TARs. You mentioned the TAR is acceptable in 0.1, 0.5 milligrams, that range. But if we run a system reliably and durably, see, you have to run not a few hours, you got to run, see, thousands of hours without stop. So I think this still requires a lot of work. What's your view about this thing? Or you have any considerations, or you have some more foreseeing points of view? Thank you.
Yes, it's correct. Now, because this system is a little complex.
I hear you.
Yes, so they're complex. So we want to separate to treat the tar and the char separately. In this case, for the tar, for example, in this area, we should consider how to control the temperature to keep the activity of the catalyst. So we also develop some catalyst here, and do some experiment on it. But sometimes maybe for 1 day, 2 days, it will deactivate it like this. So it's also some problem, yeah. Another for this system, we had ever tried to run it after 8 hours, maybe contain stable operation about 8 hours. But after 8 hours, maybe some parts will be closed by the particles. Yeah. For example, this area is very easy to be closed.
Yes.
By the sand. Yeah. So we consider because now we consider how to get the optimum pipe size in this area.
Also, in the flue decibel gasifier.
Here is
the char and those under, because the flue decibel is gasification is under reducing environment. And also biomass char is so prone for slugging and agglomeration of the ash particles of agglomerate. So I have never seen such a fluid-bed gasifier running biomass for so long and reliably. So what's your approach for this here?
Here, when we do it, it's no problem. Here we have a special structure in this area. In this area, we can let the sand can move smoothly to here.
Okay.
So here have no problem. No problem is this area. This area.
Okay.
Yeah.
Thank you.
Yeah. Thank you for your question.
Okay. Thank you much, Professor Kuan. Now is time up. We will move to next speaker. Thank you much for your nice presentation.
Oh, thank you.
So the next speaker is from Thailand, Professor Chawrit Ngam Jarasi Vichai. He's a professor from the Department of Chemical Technology, Faculty of Science, Chulalongkorn University. I would like to introduce a bit briefly about Professor Chawrit. He graduated a bachelor degree in chemical engineering from Department of Chemical Technology, Chulalongkorn University. And after that, he studied master and PhD at the University of Tokyo in applied chemistry. He started his career in Department of Chemical Technology as assistant professor at Chulalongkorn University from 2008. And after he got the associate professor in 2015, and now he's a professor in chemical engineering at Department of Chemical Technology, Chulalongkorn University. Professor Chawrit, he got many awards from many organizers, and also he published many papers. So today he will present in the title "Natural Rubber as a Renewable Carbon Source for Functional Mesopolar Silica Nanocomposites." Please welcome Professor Chawrit Ngam Jarasi Vichai. Okay.
Yeah. Can you hear me?
Yes.
Yeah. Thank you very much, Professor Chanatip, for your
please share your
introduction.
screen. Oh, yes.
Okay.
Okay.
Can you see my screen?
Yes.
Okay.
Great. Okay.
Okay. Actually, my talk today is about the concept to use natural rubber as the renewable polymers for the preparation of mesoporous organic silica nanocomposite, and then convert the rubber phase inside this precursor into carbon to obtain the mesoporous carbon silica materials. And actually, when we the porous organic silica nanocomposite are a class of material that's quite interesting in the area of catalysis, absorption, and drug delivery. And this kind of material contains both organic phase and silica matrix. The polymer or organic phase will provide the hydrophobic properties and also chemical stability, whereas the porous silica matrix will provide the high surface area of the material and also tunable pore size or narrow pore size distribution. There are many possibilities to prepare this kind of nanocomposite. Anyway, what we have to concern about this is how to homogeneously disperse the organic or polymer phase inside the mesoporous silica matrix. Because if we don't do it properly, it can affect the mass transfer properties of the resulting materials. I will introduce you one of interesting work from Professor Fujiwara's group. His group prepared mesoporous silica polysulfonate composite materials. As you can see in this slide, that the polysulfonate polymer dispersed in the silica framework of mesoporous silica. The material often had high hydrophobicity, high surface area, and even incorporate the polymer inside the silica matrix, the mesostructures still retain. And the presence of sulfuric acid group generate the acid site with high strength. Anyway, by using this material in the Friedel-Karp reaction to test the catalytic property of this material, it proved that some acid sites are embedded in the silicate pore wall. So the acidity and catalytic performance of this material are not high as expected. In our study, we try to use natural rubber as the organic phase and try to disperse the organic phase, this phase inside the mesoporous silica. Natural rubber is a polycis-1,4 isopene that obtained from heavy bacillus tree. As you may know that Thailand is the world's largest producer and exporter of natural rubber. Natural rubber has a good property in sense of high elasticity, high tensile strength, and is high resistant to fatigue from wear, and also high hydrophobicity. So it can be used for manufacturing of various products. Our study used mesoporous silica named hexagonal mesoporous silica, or HMS, as the main silica matrix. HMS is characterized by the cross-link frameworks. It has thick framework wall, high thermal stability, and it's quite easy to remove the template of HMS to prepare the porous material. So HMS is one of the mesoporous material that used in the field of absorption, catalysis, and drug delivery. Generally, the preparation of HMS use organic amine, like a primary amine, dodecylamine as the template. So once dodecylamine is dispersed in the solution of ethanol and water, it will form micelle. After addition of TRs and do the hydrothermal aging, we will obtain as synthesized HMS. And the template inside the HMS can be removed by extraction using ethanol or acidic ethanol, and also can be removed by calcination. And the mesoporous carbon silica nanocomposite is another material that's quite interesting that can be used as a host for the catalyst preparation, especially in the field of biomass conversion under aqueous phase condition. Because in every aqueous phase condition, the catalyst must contain some hydrophobicity to retard the activity of water. And also in case of carbon silica nanocomposite, the presence of carbon can generate the hydrophobic surface on this catalyst, and also can enhance the absorption of organic substrate on the catalyst. And besides these properties, once we graph the sulfuric acid group on the mesoporous carbon silica nanocomposite, it will generate the surface acidity that quite has high strength and can be used in various types of organic reaction in field of biomass conversion. First, in our study, we synthesized NR-HMS precursor by swelled NR sheet in TRs for overnight, and the swollen NR will be dispersed in the THF or tetrahydrofuran to obtain the NR solution. Then after adding dodecylamine, TRs, and water and do the hydrothermal aging, we will obtain as synthesized NR-HMS as the precursor for the preparation of mesoporous carbon silica nanocomposite. As you can see from this photo, this one is the NR sheet that we have to cut into the 1 to 1 centimeter before swelling, and then after this part NR swollen NR in THF, we will obtain the homogeneous solution like this. And after adding of water, the silica will be precipitated. The resulting NiHMS precursor will be the powder like this. In this study, we will also vary the content of natural rubber, okay, to optimize the amount of carbon in the composite material. As to give you an idea about the properties of NiHMS nanocomposite, so we show you here the TEM image of NiHMS precursor after staining with osmium tetroxide vapor. As you can see from this TEM image, it contains natural rubber lamellar phase that highly dispersed in this nanocomposite. The size of lamellar length is around 10 nanometer. That's quite correlate inconsistent with the literature report in this field. After that, we convert the NiHMS precursor into the carbon silica nanocomposite by using carbonization process. Before the carbonization, we have to pre-treat the NiHMS precursor with sulfuric acid ethanol solution. And after pre-treatment, the carbonization process will be carried out under argon atmosphere at various temperatures to optimize the synthesis condition. You can see from this photo that the color of the carbon silica nanocomposite vary with the carbonization temperature. Okay, so we can see from this that the carbon residue increase with the carbonization temperature. After that, we characterize the MCS material or carbon silica material by using various techniques. First, we start with the XRD analysis to analyze the mesoporous, the mesostructure. You can see that compared to the pure silica HMS, incorporation of natural rubber and carbon phase will decrease the intensity of the structural order. Anyway, the resulting material still retain mesostructure. By using nitrogen absorption desorption measurement, we obtain the isotherm of this material that are the typical type 4 isotherm, which can indicate the mesoporous nature of this material. The best surface area of this material are in the range of 500 to 7 something square meter per gram. It also has high total pore volume, and the pore diameter is in the range of 2 nanometer. By using in-situ FTIR, we observe that the pristine HMS has a high content of silanol group. So after incorporation of natural rubber in the NiHMS precursor, the amount of silanol group decrease. When convert NiHMS precursor to MCS material or carbon phase, the silica, the silanol group, the amount of silanol group is further decreased. And when we use the thermogravimetric analysis or TGA to quantify the amount of carbon, we found that by varying the concentration of sulfuric acid used in the pretreatment and also the temperature used in the carbonization process, we can optimize or vary the carbon content of the material. And the highest carbon content that we obtain is 16%. By using Raman spectroscopy, we can observe the peak of graphitic material and also amorphous carbon. Actually, when increase the concentration of sulfuric acid and temperature used in the carbonization, the graphitic nature of the material of carbon material increase. And when we compare this spectrum with the literature, we can say that the nature of carbon material in this MCS material are graphene-like oxide, graphene oxide-like carbon. And from the XPS study, we found that the surface of carbon contain many oxygen-containing groups, especially when we increase the concentration of sulfuric acid used in the pretreatment, and the amount of oxygen-containing group also depends on the carbonization temperature. Finally, we analyzed our material by using water absorption measurement. The pristine HMS is the surface of pristine HMS contain a lot of silanol groups, so its surface is hydrophilic. It absorbs a lot of water, and after incorporate the natural rubber into the HMS, the amount of water absorbed decrease, and then when convert the natural rubber into carbon phase, the amount of water absorbed is further decreased. As you can see from this table, the amount of water absorbed and also hydrophilicity of the material can be tuned by varying the concentration of sulfuric acid and also the temperature used in the carbonization process. In conclusion, I will talk about the formation of this material by using this scheme. First, we prepare the NiHMS precursor by disperse natural rubber in TOS, and then dissolve this gel inside in the THF to obtain the natural rubber solution. And after adding dodecylamine water and additional TOS, we will obtain NiHMS precursor. The NiHMS precursor will be treated with sulfuric acid ethanol solution to extract the template from the NiHMS precursor. And from the study and characterization, we believe that sulfuric acid will work as the catalyst to promote the carbonization. So after carbonize the NiHMS precursor at different temperature, we will convert the rubber phase into carbon, and the nature of carbon phase dispersed in the MCS material will depend on the temperature used, and the temperature used also determine the functional group that present on the carbon phase. So finally, I would like to thank all these organizations for the financial support and also the technical support. Thank you for your kind attention.
Thank you very much, Professor Chawaris. Are there any questions from participants? Let me check the chat box. So I have one short question. How about the mesopolar structure after carbonization? Is still present the mesopolar structure?
Yes. So we prove the nature of mesostructure of this material by using XRD. And you can see that the MCS material still show the 100 peak. That is the typical for the wormhole-like mesostructure material. It's similar to HMS, but the intensity decreased because the incorporation of carbon will decrease the arrangement of the mesopore.
Okay. So any more question? So
I have
if
a question.
yes,
Yes, one short question. Thank you very much, Professor Shawalit, for nice presentation. In this work, you use a natural rubber, right?
Yes.
This one use a natural rubber latex for the
No,
template.
we use NR sheet.
NR sheet.
Yes, yes.
Okay.
And we also try to use natural rubber latex. The research is ongoing.
Mm-hmm. Yes, and how to control the size of the natural rubber to make as a homogeneity of the template.
You mean in case of NR sheet?
Yes.
Actually, we have to ensure that NR sheet dissolved, totally dissolved in THF. So from this study, we try to optimize the natural rubber content in HMS precursor by varying the content from 0.5 to 1.5. We found that the range of rubber that can incorporate to the NiHBA precursor is quite limited. So when we start with 1 or 1.5, we observe the excess amount of natural rubber. So it can observe by visual and not powder like this. It forms something like the agglomerate that separate from the powder phase.
I see. Okay, thank you very much.
Yeah, thank you.
Okay. Thank you much, Professor Shawalit, for your nice talk. Thank you much. So we will move to next speaker. The next speaker is an oral contribution. So you will have 10 minutes, including question and answer. The first oral contribution is Mr. Asika Anywhere from Hirosaki University. He will talk about the co-gasification of Japanese cedar wood and its commercial biochar for hydrogen-rich gas production via steam gasification process. Please.
Can you see my screen?
Yes.
Okay. Good afternoon and good evening, everyone. My name is Askar Anwar from Hirosaki University in Japan. And today I would like to present our recent research about co-gasification of Japanese cedar wood and commercial biochar for hydrogen-rich gas production via steam gasification process. So let's see the energy status of Japan. So we can see from the figure, the self-sufficiency ratios of energy in Japan decreased more than 10% in these several years due to the impact of the great earthquake happened in 2011, which consequently increased the dependence on fossil fuels. And we know almost all the fossil fuels in Japan are imported, and also Japan is planning to build a hydrogen society. However, most of the hydrogen is produced from natural gas and also the coal. So in our study, we would like to utilize the domestic biomass resources to produce hydrogen-rich syngas from by the gasification process. So for the biomass resources in Japan, the most abundant biomass resources should be the woody biomass because of the large forest area and also the large architectural waste wood production per year. So in this study, we use the Japanese cedar wood, which is carbonized in a rotary furnace at 720 degrees Celsius in 2 minutes and to produce the commercial biochar. And this kind of biochar currently is utilized in the agriculture field for soil treatment. So we want to investigate if this kind of biochar can be utilized as the gasification feedstock. So here we can see the photos of the raw materials and also the commercial biochar. Both of two samples were cut to the small size that is easy to put into the reactor tube. And also we conducted the ultimate analysis, proximate analysis, and also XRF analysis. So we can see from here, actually after the carbonization process, the cedar wood turned into like pure carbon materials. And also the large content of calcium and potassium were contained in their ash. We know these two elements are good for the gasification process. And here is our experimental apparatus and conditions. So we used the vertical lab scale fixed back reactor, and 0.5 grams of samples used in each experiment, and the experimental time we fixed to the 200 minutes. So before the gasification process, we did some analysis to understand the characteristic of the biomass and biochar. So in the TG analysis in the nitrogen atmosphere, we can see actually the biochar showed a higher heat resistance after the carbonization process, and also the higher fixed carbon content. And in the air atmosphere, we can know the ash content of two samples, and the ash content are both low in these two samples, which are also the common characteristic for the woody biomass. And also we did the SEM and also BET analysis. So we can see actually after the carbonization process, the surface of the cedar wood decomposed and show the inner porous structure. It's a really good structure. It's good, easily to react with the steam, and also the BET surface area also increased significantly after the carbonization process. So here is the gasification results of two individual samples. So the gas yields from two samples increased with the temperature and show the highest gas yield at 850 degrees Celsius. And for the raw biomass, we can see the conversion rate is quite high even at low temperature. But the problem is the carbon conversion efficiency is really low, which means large content of tar produced from the raw biomass gasification. However, for the biochar gasification, only at the 650 degrees Celsius show the low conversion rate because the temperature is lower than the carbonization temperature. And the carbon conversion efficiency increased significantly with the temperature, and we know and less tar produced from the biochar gasification. So, and then we tried to mix the biomass and the biochar together to conduct the co-gasification process. And we mixed the two samples in 3 different ratios. And we can see at the mixing ratio for the 1:1 and 1:2, we can obtain the synergistic effect in these two mixing ratios. And we assume that the synergistic effect might be attributed to the tar conversion because the raw cedar wood tend to produce tar, and the tar might be converted by the biochar to the syngas. So in order to investigate the synergistic effect, we further conduct the TG analysis on blend samples. So we put the two samples up and down differently So from the TG results, we can see when we put the biochar on the top of raw cedar wood, actually we can get the more solid residues left, which means the possible mechanism might be the tar generated from the bottom part of the raw cedar wood, passing through the char bed and captured by the char matrix and converted to the light gas, and also leave the soot on the surface of biochar. And this kind of soot or coke actually in the steam atmosphere can react with the steam to produce the hydrogen or carbon monoxide. So this might be the mechanism. So here is the conclusion of this work. So most of the volatile matters of cedar wood were removed during the carbonization process and formed the biochar with high fixed carbon content. And the steam gasification of raw cedar wood tend to produce large content of tar, while the steam gasification of the biochar prefer to produce hydrogen-rich syngas. And the synergistic effect was obtained by co-gasifying the raw sample and the biochar with the mixing ratio of 1:1 and 1:2. So the synergistic effect should be attributed to the tar produced from the raw biomass was catalytically reformed into the hydrogen-rich syngas by the biochar. So however, increasing the amount of raw biomass in the mixture sample led to the coke deposition on the surface and covered the activist site of the biochar, and also decreasing the gasification reactivity of the biochar sample. That's all. Thank you. Thanks for your attention.
Thank you very much. Any question from participant?
Hello, can you hear me?
Yes.
I have a question. Thank you for your nice presentation, Oscar. I want to know that for the co-gasification of wood and the biochar, you proposed a mechanism, right?
Yeah.
Maybe in the mechanism you mentioned that maybe the different flow of the gas from tar through the char bed may because of this it can result in the tar to.
Yes. Oh.
Okay. Are you be there?
No sound.
Yes.
Yeah.
Okay. Maybe some problem about the internet.
Maybe let them discuss later.
Okay. So going to the thank you much, and we are going to the next speaker. So if you have any question, please direct message to him.
Thank you very much.
Okay. Okay. So we are going to the next speaker. Also from Hirosaki University. Yes. Okay. Yes. So today she will present in the title hybrid coal production from low rank coal and mahogany sawdust using semi-double chamber reactor. Please.
Yes. Sorry, can you see my screen?
Yes.
Okay, I will start the presentation. Thank you very much. I am Zara from Hirosaki University. So in this moment, I will present about our works entitled Hybrid Coal Production from Low-Rank Coal and Mahogany Sawdust using Semi-Double Chamber Reactor. So for the background, the current situation of Indonesia coals is Indonesia has a lot of reserves and resources, but 70% of the resources is categorized as low-rank coal. And low-rank coal actually has some concern that are high moisture content and it has low calorific value, low efficiency during processing, high transportation cost, and also high carbon dioxide emission during the processing. This is why the low rank coal is not really preferable compared to the higher rank coal. While Indonesia also has a lot of biomass that can be used for fuel resources, because biomass is categorized as environmentally friendly fuel resources because of its natural carbon dioxide emission and low sulfur content. And biomass also also known as a carbon neutral fuel source because of the amount of carbon dioxide released during thermal processing will be equal to the amount of carbon dioxide removed from the atmosphere by photosynthesis throughout the life of biomass, so that the carbon footprint for biomass can be assumed zero, while the carbon footprint means the total amount of greenhouse gas emission that released over a certain period of time. And combining low-rank coal and biomass using process called co-pyrolysis, which is a thermal decomposition without or with a minimum amount of oxygen, can produce a new fuel that can be called as hybrid coal. Hybrid coal has several benefits compared to its parent coal, that are the calorific value that is increased, the moisture content that would be decreased, and also it can increase the hydrophobicity of biomass, so the decaying is inhibited, and then it can decrease non-neutral carbon dioxide emission because the utilization of biomass waste and the possibility of synergistic effect, and also it can increase the economic value of utilizing biomass waste into a more valuable product. So this is the reactor that we use to produce the hybrid coal, that is a semi-double chamber reactor. So why it's double chamber? Because it has two different chamber. The first chamber is the inner chamber, which is the co-pyrolysis chamber, where the co-pyrolysis of coal and biomass happened. And the outer chamber is the combustion chamber. So since the co-pyrolysis needs heat, so we provide the heat from the combustion of biomass. And the air for the combustion comes from the bottom, and the gas comes from the upper side of the reactor. And the reactor itself can be categorized as a semi-pilot reactor. So the aims of our study is to determine the variation of the feed or the blends of biomass and coal versus the fuel or the biomass that is used for the as the heat resource ratio. And then we also want to determine the feeding method. The feeding method that we means is that we compare two different kind of feeding. So for the combustion, in this method, the single feeding method means that all the fuel that is combusted put before the co-pyrolysis began, while the double feeding method, we divide into two different batch. So the first batch will be before the co-pyrolysis happened, and the second batch is during the co-pyrolysis. And then we also want to calculate the reduction in non-neutral carbon dioxide for the utilization of hybrid coal versus the raw coal. And the coal that is used is a bituminous coal, while the biomass is mahogany sawdust. So this is the experimental step. It includes the drying of biomass, and then the reducing the coal and biomass size, and then mixing, and then continue to granule, and then the co-pyrolysis itself and the characterization. So in the reactor, we installed two thermocouple from inside the co-pyrolysis chamber and named T2 and T3. And during the co-pyrolysis, we try to observe the temperature. So in this graph, this is 1/3 feed fuel ratio and single feeding. We can find one peak here, while if we use a double feeding method, we can find two peaks in the temperature. And the pyrolysis zone is a zone where the pyrolysis happened. It started from 200 degrees Celsius above. So, and the next is the proximate analysis. So in general, the fixed carbon content and calorific value of hybrid coal shows an increase in line with the increase in amount of fuel use. So this means that if we use more fuel, for example, 1/5, the amount of fixed carbon will be the highest one compared to 1/3. While comparing the single feeding and double feeding, the double feeding resulting in a more fixed carbon content, which means that the heat that is provided in the double feeding and the higher fuel amount is higher, so that the volatile will be really small compared to the lower variation. And also for the calorific value, comparing the hybrid coal versus the original coal, we can see that the calorific value is increased. Also, the highest one is this variation, which also can be categorized as bituminous C class coal, while the initial coal only as bituminous C. While for the product yield, the higher the fuel that is supplied, the lower solid yield of the product. And also comparing to different feeding method, the single feeding method, the double feeding method, actually resulting in a higher, the single feeding method for 1/3 resulting the highest yield compared to another variation. And for the carbon dioxide emission reduction, so in this calculation, we try to compare if the hybrid coal is used, for example, in the combustion in the power plant, compared to the use of the raw coal for the same amounts of energy supply. And we can see that there will be like about 30% of the emission reduction in carbon dioxide. So actually the main concern of this reactor is that we cannot control the amount of heat provided, so that while we also want to maximize the value of solid yield, so we want to maintain the temperature between 200 and 300 degrees Celsius. While in single feeding method, in this graph, you can see that the overshoot is up to 450 degrees Celsius, while for double feeding method is up to 400 degrees Celsius. So we want to find the optimum way to maintain the temperature. So we try to introduce the intermittent feeding. So the intermittent
excuse me, you have 1 minute. Please wrap up your talk.
Okay. So for the intermittent feeding method, it resulting the lowest overshoot temperature, and also it has higher solid yield compared to the single feeding and the double feeding method. So the conclusion of this study is that the production of hybrid coal can improve the coal quality in terms of the calorific value of raw coal. And hybrid coal has a higher coal rank compared to the raw coal that can increase from bituminous C up to bituminous C. And the variation that resulting the most optimum result is in ratio 1/3 with the yield of 53%, and the most optimum fuel feeding method is the intermittent feeding that resulting in a more controllable co-torrefaction environment. Thank you for your attention.
Thank you very much. I'm sorry, though we don't have time for question and answer. So if you have any question, you can send direct message in chat box. So we will move to next speaker. Thank you very much for your presentation. We will move to next speaker, please.
So the next speaker is the Hu Kuiyang from Taiwan University and Technology. Could you share your screen?
Yes, I can speak.
Yes.
Okay, good afternoon, everyone. My name is Hou Qiwang, and I come from Taiwan University of Technology. The topic of my report is the design and evolution of a core-based polygeneration carbon circle system. Mainly introduce my work from these four aspects. First of all, the background. In 2020 years, China proposed a carbon peak and a carbon neutral goal. In order to achieve this goal, we need to formulate a timetable, road map, and construction drawing in the power plant, building, chemical industry, and agriculture. So how does the reform of the core chemical industry develop? As can be seen from the chart on the right, China's energy consumption structure is still dominated by coal. In order to achieve the dual carbon goal, the coal used for power generation will decrease, and the core chemical industry will continue to grow. Therefore, core based polygeneration system has become an effective measure for clean and efficient utilization of lowering coal. China has huge reserves of low coal. The lowering coal generation system is divided into partial pyrolysis, partial gasification, pyrolysis, and for gasification from the gas source. The picture on the right shows some polygeneration systems. Next, we will introduce the gas head. There are some problems in the grading utilization of coal. Professor Tsumi of Japan proposed a three-bed combined circulating flow desired bed. As shown in the picture on the right, our research group has also conducted some research on TBCFB. The picture on the left is a road map for carbon capture, utilization, and storage. This red route is a low carbon route. Let's introduce the second part. From the previous introduction, we found some problems in the research of polygeneration system. To solve this problem, some solutions are proposed, as shown in the table on the right. This is my research idea. Mainly applying the new technology and the new cycle to the core-based polygeneration system. and determine the optimal operating conditions of the system with the goal of energy utilization. Through the exergy analysis, the unit with the highest exergy load in the system is found. And finally, the system is systematically performed performance evolution. The following figure is a process diagram of a core-based polygeneration system that can be seen from the figure. That the first circle is the pyrolysis gas circle generated by pyrolysis as the pyrolysis atmosphere. And a part of pyrolysis gas is sent to the gas tube for combustion. We use the oxygen enriched combustion. The carbon dioxide concentration in the flue gas at the combustion outlet reaches more than 95%. And the flue gas preceded by the combustion is directly used as the working fluid of the power plant. This is a core and this is our selected core simple and industrial element analysis. Next, I will introduce the third part. The picture shows the flow chart of the core-based polygeneration carbon circle system, which is mainly divided into a gasification unit, synthesis unit, purification unit, a distillation unit, power unit, and air separation unit. The picture mainly analyzed the synthesis gas circulation ratio and the flue gas injection value that affect the system. A suitable circle ratio and the flue gas injection rate are abundant. We use the second chart to show the material and the energy balance of the system, and we can clearly see the direction of the material and the energy in the system. The picture on the left is the exergy diagram of the system, and the picture on the right is the exergy efficiency of each unit of the system. We know from the exergy analysis, the gasification unit has the largest exergy load and the lowest exergy efficiency. The gasification unit is the weakest link in the system, and the exergy efficiency of the gasification unit needs to be further improved. We compare core-based polygeneration carbon circle system with a traditional car-based polygeneration system without a pyrolysis circle. We find the core basic polygeneration carbon cycle system has higher energy and exchange efficiency. We compare the CBPCC system with the Sprint production system, and the relative energy saving rate is 13%. Finally, we have the following conclusions and perspectives. Taking the system energy efficiency as the goal, the circle ratio is 1.05, and this carbon oxide rejection amount is 30,000 as the optimal operating conditions. Thanks. My report is over.
Thank you very much for your presentation. If any participant have any question, can you put in the chat box or can put the emoji hand up? So during the time is limit, so if you have any question, you can direct to the presenter and we can move to the next presentation. Thank you very much.
Okay,
for the next presentation is Liang Fu from Shenyang University of Chemical Technology.
Okay, can you hear me?
Yes, everything is fine. Yeah, can you start?
我的声音没开。Can you hear me?
Yes.
Okay, I'll begin. Good afternoon, everyone. I'm Liang Fu from the Shenyang University of Chemical Technology. The topic of my report is characteristics of cryptocrystalline magnesite particles centered in fluidized bed. Many reports from these four continents. Magnesite is mainly distributed in 6 countries, including China, North Korea, Russia, Slovakia, Brazil, and Australia. And the reserves in these 6 countries exceed 19%. Among them, China supplies over 17% of the world market. According to the grain size, there are 2 kinds of magnesite: cryptocrystalline magnesite and macrocrystalline magnesite. Among them, China's macrocrystalline magnesite is mainly distributed in Liaoning province, while cryptocrystalline magnesite is mainly distributed in Qinghai and Tibet. We can see from the magnesite application that most magnesite is processed into dead bronze magnesia and used as refractory. The picture on the left shows the traditional production process of dead bronze magnesia. We can see that magnesite is milled, screened, molded, sintered at high temperature, and crushed. The process is very complicated and not environmentally friendly. The core equipment of the process is a high temperature soft kiln, influenced by fuel injection points and airflow distribution. The temperature distribution in the furnace is uneven, especially This is a great temperature difference between inside and outside the particle, the pellet. In actual production, the quality of the products is guaranteed by continuously increasing the sintering temperature and prolonging the sintering time. However, doing so leads to low production efficiency and increased energy consumption. Through SEM inside and outside the magnesia product, we can see gas in the pellet. In the sintering process, the outside of pellet is heated up and sintered into a dense isolation layer, which hinders the transfer of heat and internal gas. It can be seen that the technical barrier that causes the low growth efficiency of magnesia at present is that the high resistance of heat and mass transfer in the sintering process is large. Through the simulation and analysis of the heat transfer dynamics of particles, we can see that it takes more than 100 times for large particles to reach the required temperature. Therefore, we proposed new technology to prepare magnesia by directly sintering magnesite particles in the fluidized bed. The new technology has the advantages of fast sintering speed, simple process, uniform quality, and low energy consumption. To verify the technical feasibility and study the sintering law of magnesite in the fluidized bed, we set up a high temperature fixed bed and fluidized bed sintering experimental device. The finger shows a high temperature fixed bed reactor, and the experimental samples are put into the high temperature reactor through poking crucible for sintering for a specific time. The left picture shows the method of fluidized bed sintering experiment. The sinter sample is taken out through a platinum crucible and analyzed by BT, SEM, and XRD. The picture on the right is a serial device for a high temperature fluidized bed sintering experiment. The following is the experimental result of fixed bed sintering. The finger shows that cryptocrystalline magnesite takes 3 hours to complete sintering, while macrocrystalline magnesite takes only 10 minutes. The fluidization stage of magnesite during sintering at high temperatures is affected by the ever-changing viscosity of particles and gas. We know the fluidization stage of particles by observing the change of bed pressure in the fluidized bed in real time and controlling by adjusting the fluidization gas velocity. From the correlation between bulk density and sintering time, we can see that the sintering rate of cryptocrystalline magnesite is lower than that of macrocrystalline magnesite. Sintering temperature has a more significant influence on the sintering of cryptocrystalline magnesite. From the microstructure of the magnesite products with 2 crystal forms fried by a fluidized bed, we can see that the microstructures of the 2 products are consistent. The grain size is larger than that of dead brown magnesia in a traditional soft cane. The fluidized bed is advantageous over soft canes in sintering cryptocrystalline and macrocrystalline magnesite because it only is a shorter time and lower temperature. From the microstructure of the sample centered in fixed bed and fluidized bed, we can see that the sample centered in fluidized bed are heated uniformly and have few cracks, so the staking density is high. The above research finds sintering of particle magnesium touch is technically feasible, and a fluidized bed produces better products than a fixed bed. Cryptocrystalline magnetite takes a longer single time than macrocrystalline magnetite in the fluidized bed, but it's still far less than that in traditional soft gain. Over. Thank you all.
Okay, thank you very much for your presentation, and we have allow 1 minute for question and answer. Have any participant have question or not? So I have one question. Why you select the temperature like 2000 degrees Celsius or 1600 degrees Celsius on the SCM image slide? On the slide 14. Can you hear me? So
Maybe you turn off your microphone. Please turn on. Mean the presenter. Maybe we move to the next one. Next speaker, please. Oh, okay. Already on.
I'm sorry, I think you asked others.
Okay, so. So maybe you ask question again.
So I want to know why you select the temperature like 1600 degrees C and 2600 degrees C on slide 14.
I'm sorry, I think you asked the next person to report. The page 14, is it page?
How did you select the temperature?
Oh, because the material of the experiment is different. The down picture, the DBM 19 inch is the product in the market, and the the first two in our experiment sample and not come from the same material. So its microstructure is a little different.
Okay, thank you very much for your answer. And so now we can move to the next presenter. Yeah, thank you very much. And the next presenter is Chao Wang from Shenyang University of Chemical Technology. Sorry, we cannot hear you. Maybe can you turn on your microphone? So now we cannot hear you.
Hello, can you hear me?
Yes, yes.
Okay. Good afternoon, everyone. My name is Wang Chao from Shenyang University Chemical Technology. My presentation is low-tar gasification of biomass using oxygen steam in a two-stage gasifier, a flow-desert gasifier. I will present my work from following 5 contents. Biomass is an abundantly solid renewable energy source. The application of biomass cycles the generated CO2 between biomass processing and growth without any greenhouse gas emission. Gas-efficient technology is regarded as best method to convert biomass as clean flue gas or syngas. However, the tar generation between drawing biomass gasification is a big challenge. Reaction developing method has been expected to upgrade the gasification technology for producing high quantity flue gas and eliminating tar. Biomass gasifiers include fixed-bed gasifier and flow-desert gasifier. With the gasifier developing from single stage to developing decoupling reaction. Tar problem is always the big serious one. To date, some factors for low tar flue gas products should be considered first. For low tar flue gas production, the generated tar must follow from the lower temperature to higher temperature, and then for lower heating value flue gas production. Flue gas should effectively avoid the dilution of flue gas or carrier gas. Tar removal method mainly include 2 rules. Outbed method, also defined as the physical treatment method. This method not only ignores the heating value of tar, but also wastes the best of water. Another method is in-bed method. This way, this method treats tar in gasifer, including thermal cracking, catalytic cracking, and steam reforming, which can improve the total gasification efficiency. We designed a pilot two-stage gasifer, coupling a donor processor and a riser gasifer for pin chips gasification using oxygen steam as gasifying agent. In the first stage, two biomass fast pyrolysis is carried out without any carrier gas, and then all the products are transported into the second stage together with heating carrier particles, which can avoid the dilution affected by the carrier gas, such as nitrogen in air. Or in the second stage, oxygen steam can promote tar reforming, and the tar steam follows from low temperature zone to high temperature zone, increasing the thermal cracking. Meanwhile, the generated hot char forms a catalytic bed, increasing the catalytic cracking. First, we did the protecting without any biomass feeding. Under steady state, the temperature of processor reached above 720 degrees C, and the temperature of the gasifer reached about 800 degrees C. And then the gasification tested. It started from feeding 5 kilogram pin chips into processor. The temperature of under the steady state, the temperature of the processor reached about 760 degrees C. The temperature of gasifer reached about 830 degrees C, and the increasing pressure in riser is caused by the generated char bed. For biomass gasification, keeping the split gas volume same in riser at 850 degrees C, the ER value and the S2B ratio are discharged by changing the oxygen and the steam concentration respectively. This gasifer with oxygen steam as the gasifying agent greatly increase the syngas lower heating volume, which reached above 10 mg per m3. Introducing steam into the gasifer benefits tar elimination. Under present conditions, the tar content in syngas reached about 1 gram per m3. The result of temperature series time series gas compositions shows the great continued steady operation and the good technical feasibility. Conclusions: the pilot cycled two-stage gasifer is set up and have good technical feasibility for continuous steady operation. This gasifer with oxygen-rich steam as gasifying agent greatly decreases the tar content in products syngas with high lower heating value from biomass, and the two-stage precision coupling to fluidizer bed reactor have great potential applications for low tar syngas production. And the way operation is directing to tar content below 100 microgram PnM3 by increasing the temperature and the ER value. That's all. Thank you. Thank you for your attention.
Thank you very much for your presentation. Now we have 1 minute left for question and answer.
Okay.
So if no question, so thank you very much for the presentation. And during the time is limit, so we can move to the next presenter. So the next presenter is the last of this section today is Bồ Wei Yan from Thuận Giang University of Chemical Technology. Can you share your screen?
Wait a moment. Can you hear me?
Yes.
Okay. Good afternoon, everyone. My name is Yan Bo. I'm a doctoral student from Shenyang University of Chemical Technology. My mentor is Guang Wenxue and Zhen Han. My research topic is fluid bed calcination of limestone and changes of chemistry and morphology of product. Carbon dioxide is a major contributor to global warming, and its emissions of coal-fired power plants account for more than 60% of total carbon dioxide emissions of fossil fuels. Therefore, it is necessary to prevent climate change by reducing carbon dioxide emissions of coal-fired power plants. A method for reducing carbon dioxide emissions is to capture then can be used to manufacture medicine, fertilizer, fire extinguisher, drinks, and steel. Carbon dioxide capture and storage technology includes. Can you hear me? Hello?
Yes, we can hear you.
Okay. Carbon dioxide capture and storage technology. Combustion. Only the technology of post-combustion is relatively mature. Among 5 industrialized post-combustion technology, calcium looping process, based on the reversible reaction between calcium oxide and carbon dioxide, is the most promising way to capture carbon dioxide. Because cheap and widely sourced limestone and mature fluid bed technology can be used, thus the energy consumption and the cost can be reduced greatly. At present, the thermogravimetric and analyzer and fluid bed are mostly used to study the influence of reaction conditions on product reactivity. The residence time is beyond several minutes. Results show that the carbon dioxide absorbability of product is between 0.08 to 0.15 gram per gram calcium carbonate, and it will decrease to 0.04 gram per gram calcium carbonate upon iterative carbonation calcination cycles. So there are 2 technical problems. Product reactivity is low, and the cyclic reactivity of product decreases rapidly. This is a diagram of pilot scale transport bed. High temperature fluid gas generated by propane combustion in furnace enters transport bed from the bottom. Limestone powder is calcined by high temperature fluid gas and entered to cyclone. Limestone powder is calcined circularly to increase total residence time. The electric heater can ensure consistent temperature field. Limestone calcination in pilot scale transport bed has 3 advantages. large heat transfer coefficient, limestone can be heated evenly. Residence time can be accurately controlled by increasing calcination times. With the above advantages, the changes of morphology and the reactivity of product can be revealed during limestone decomposition in pilot scale transfer bed, so as to provide better understanding of why cyclic reactivity of solvents decreases rapidly in industrial calcium looping process. The reaction temperature is between 800 to 900 degrees. The residence time is between 2.12 to 2 seconds in single calcination. The limestone used in experiment was from China. The content of calcium carbonate is 92%. TG, SRD, BT analysis, and scanning electron microscope were used to characterize the product. The results show that the decomposition degree of limestone increases with the increasing of reaction temperature and residence time. When residence time exceeds 10 seconds, the decomposition reaction of limestone is controlled by heat and mass transfer. When residence time exceeds 16 seconds, the influence of reaction temperature on decomposition degree of limestone decreases with the increasing of particle size. The decomposition of limestone is approximated as a spherical model. The conversion rate decreases with the increasing of decomposition degree. When decomposition degree reach 80%, the conversion rate decreases to 0.02 per second. This indicates that the influence of heat transfer and carbon dioxide diffusion are still obvious, even for very small particles, and it is necessary to increase reaction temperature or residence time to promote further decomposition of unreacted core. With the increasing of residence time, the intensity of peaks of calcium oxide increases and that of calcium carbonate decreases. When the residence time exceeds 16 seconds, there are still diffraction peaks of calcium carbonate exist. And the green side of calcium oxide increases gradually. This indicates that the decomposition reaction of calcium carbonate occurs simultaneously with the green growth of newly formed calcium oxide crystal. On the other hand, the green size of calcium oxide increases obviously with the rising of reaction temperature. That might be because the rising of temperature promotes lattice diffusion and is in favor of agglomeration of calcium oxide. With the increasing of residence time, the peak of process distribution increases gradually. When reaction temperature is 800 degrees, the pore volume increases continuously and the specific surface area increases first and decreases slowly. Whereas under 900 degrees, the pore volume is relatively stable and the specific surface area decreases continuously. When residence time exceeds 6 seconds, both pore volume and the specific surface area decreases with the rising reaction temperature. A dramatic change of surface morphology of product occurs within a few seconds during limestone calcination at 800 to 900 degrees. In the early stage of calcination, a pore structure can be found on product surface due to the release of carbon dioxide, with a further increasing of residence time. The green size of calcium oxide crystal and process begin to grow gradually due to the sintering. It can be seen that the sintering is promoted by the rising of reaction temperature. We can see that reaction temperature has an obvious effect on carbonation reaction in flask reaction regime. That might be because the sintering of particles is promoted by the rising of reaction temperature, leading to the decrease of both pore volume and the specific surface area. On the other hand, the carbonation curve moves towards high temperature field gradually. The reason might be that the amount of small pores with a diameter less than 20 nanometers, which strongly influence conversion rate at primary carbonation reaction stage, decrease with the increasing of residence time. And the moving amplitude increases with the rising of reaction temperature. The reason might be that when the reactor temperature is 800 degrees, the pore volume increases continuously, and this is in favor of carbonation reaction. Whereas at 900 degrees, there's no obvious change in pore volume. Within just a few seconds, a high calcination temperature will greatly promote the sintering of particles and then decrease product reactivity sharply. With the increasing of reaction temperature from 800 to 900 degrees, the carbon dioxide absorption ability of product decreases from 0.21 to 0.15 gram per gram calcium carbonate. This indicates that the calcination temperature has a dominant effect on the carbonation performance of calcium oxide-based solvents. Even at the same decomposition degree of limestone, the rising of reaction temperature significantly decreases both maximum carbonation conversion and carbon dioxide absorption ability. On account of that, decreasing reaction temperature by reducing partial pressure of carbon dioxide might be the most effective way to resist sintering of solvents in industrial calcium looping process. Findings: a dramatic change in surface morphology of product occurs within a few seconds during limestone calcination in pilot scale transport bed and 800 to 900 degrees. Second, within just a few seconds, an extreme high calcination temperature greatly promotes the sintering of calcium oxide and aggregation of crystal, and then reduces the product reactivity sharply. The calcination temperature has a dominant effect on carbonation performance of calcium oxide. A mild reaction condition can enhance the durability of calcium oxide-based solvents by reducing the partial pressure of carbon dioxide during calcination. For example, introducing steam into calcination atmosphere. Thank you.
Thank you very much for your nice presentation. And we have a little bit time for question and answer.
I have one short question. So how about the reusability of calcium oxide is when you capture CO2?
Will you ask it again?
About the reusability of calcium oxide when you capture the CO2, right? You dissolve it, and after that you absorb again, right?
Yes. Carbon dioxide is used to absorb carbon dioxide.
Yes, can it be used?
In this research, we focus on the reactivity and morphology of calcium oxide in industrial calcium looping process. Let's just absorb carbon dioxide in coal-fired power plant. That's all.
So, okay.
That's all.
Okay, I think no question, Dr. Suchada.
Yes, so if no question, thank you very much for your presentation. And so the section for present today, it will finish.
Yes, before we close the session, so we have some announcement. The next session will be the committee meeting. If you interested to share about the YSCRC Symposium, please join the other Zoom meeting that show in the chat box. So we still have 2 days for our symposium. Tomorrow we will start 1 p.m. in Thailand time, so 2 p.m. in China and 3 p.m. in Japan. So we will start with the plenary lecture. Professor Raphael Luque, the editor-in-chief of molecular catalysis. So, and also we have an invited speaker for tomorrow. So for today, thank you very much to join our symposium. I would like to close the the session, and see you tomorrow, and stay safe for our pandemics. Thank you very much.
Thank you.
See, bye bye. See you.
Thank you.
Thank you. Thank you.
Yes, for the committee meeting, we are going to next link. Not the link. You can leave this Zoom meeting and join another link. Okay. See you in another link. You can use in the chat box. You can see the link. Okay. So see you in the committee meeting. Goodbye for today.
Okay. Done. Go home.